system, but not for this system. And that is, if we look at this, for this first system, A1 is equal to 0. So what does that mean? It means that this term drops out. So we have originally this real term and then plus or minus these guys, which are either going to form a complex conjugate pair or be a positive and negative real number. So what that means is that if A1 is equal to 0 and our system is originally unstable, then there's actually no way for a constant k to stabilize our system, because we don't get anything out of this term. And then for this term, we start off being unstable. Again, I should add, if this is originally a complex conjugate pair, then either it remains a complex conjugate pair, or it remains purely imaginary if the argument of this square root is negative, or if it becomes positive, then one of these guys is positive and one of them is negative. So either way, you don't get more stable. So again, it's relatively simple to see from this equation that there's actually no way or no constant k that is going to stabilize this P1. On the other hand, with P2, we're kind of saved by the fact that we have this term here, which has a negative out the front. So what that means is that k actually makes these poles more negative, at least in terms of this contribution here. It's a little bit more complicated once we add the effect of this, but it's feasible that we should be able to control the system in this way. Okay, so again, to summarize, for a positive A1, which is what we had for this second system, a positive k will tend to move the eigenvalues towards the left half plane, so to stabilize it, which is why we stabilize system 2, but not system 1. Okay, so that is nice. It turns out that it's relatively easy to understand what we had observed empirically. But now the question, or now one question that we can ask is, well, how do we stabilize this system? So one thing we could do is, and there are obviously a lot of things that we can do, and eventually we'll introduce a lot more theory that will allow us to perhaps do this in more systematic ways. But one thing that we could do is actually choose a controller that makes system 1 kind of look more like the controlled version of system 2. So that is, if we choose a controller that basically replaces this numerator with this numerator, then I'm actually going to get a system that should have the same poles. So in other words, I get the same 1 plus pk equals 0 equation for system 1 if I choose a controller that looks like this. And again, this is not necessarily the smartest thing to do, but what we can do without knowing anything else or developing any other theory is we can use the fact that we know that our controller works for a similar system, or use the fact that we know that a k equals 1 proportional controller works for a similar system to find what can be thought of as an equivalent controller to stabilize our system 1, which proved to be a little bit trickier to control. So in practice, what I can do now is define a new controller for our system 1, where, again, I'm putting my open loop system in feedback with a k, but now my k is a transfer function. So it's not a proper transfer function because the degree of the numerator is greater than the degree of the denominator, but that's okay. And so what I can do is run this. I can look at what I get, and at the end of the day, if I look at my transfer function between my new controlled system 1 and the controlled system 2 with k equals 1 down the bottom here, I see that they have the same denominators. So the numerators are still different, but at least I've managed to put my poles sort of where I want them, or where they'll be stable. And there's sort of a technicality here in terms of basically to do this feedback, I had to go to transfer function notation because Python doesn't like non-proper systems in state space form, and then I had to adjust my state because it kind of changed. But that's a minor technicality, but at the end of the day, when I simulate this system, I now have a stable response for both of my systems. So that's nice. So again, I'm turning on control at a particular point. The orange curve is the original system 2, which was stabilized with k equals 1, and then the green curve is that controller that I designed to try to get a system that looked kind of like system 2 when it was controlled. They're different, though, again, because the numerator of the transfer function is different. Are there any questions so far? Okay, good. So we're going to do things a bit more systematically now. But I'll mention that really what we've started to do is look at some special cases of PID control. So that is where we have a controller with relatively simple dynamics that includes a proportional term, a derivative term, and those two are what we have here. And then we can also have an integral term. And so intuitively what's going on here is that we're taking our output and then we're saying that our control input, or the input to our system, is going to be a function both of that output and then also its integral and or derivative with time. Or in other words, if let's say our output was sinusoidal, say, then we're really sort of shifting in phase to get the derivative and the integral terms. And there are many ways and rules of thumb that one can use to tune these parameters. This type of control is still used a lot in industrial applications, for example. It's relatively simple. If you know what you're doing, it can work relatively well. Sorry, that should be a D, not a P, I realized. But it still requires potentially some sort of guessing or sort of twisting of knobs to obtain some desired behavior. And so and again, I could go back to the notebook and start playing around with these things. But in the interest of time, we'll keep pushing through. But feel free to play around with that yourselves. Okay, but more generally, if I have, say, a simple controller, I might want to be able to predict something about the performance or the stability characteristics of my closed-loop system. Now, in the example that I showed, it was actually relatively simple to, from first principles, determine where my closed-loop poles were. But that really relied on me only having a two-dimensional system which had a quadratic that I needed to solve for the poles, and I could use my quadratic formula, and so everything works out nicely. More generally, though, if we had a higher order system, so that is if the denominator of our transfer function was a higher order polynomial, then it quickly becomes intractable to solve. And so that motivates sort of the design of tools that can help us make these predictions without having to do the precise math. And so that motivates the root locus plot. And so what this is it's a plot of all of the poles, all of the closed loop poles that you get that are parameterized by some constant within some controller. So most simply, this could just be proportional control and looking at all non-negative constants of proportionality. Or more generally, if you can take a factor of k out of your controller, so that is, let your plant multiplied by your controller be equal to k multiplied by some other transfer function, then you can do things that way as well. And so it will turn out that it's actually possible to look at what these root locus plots look like, say in Python or MATLAB, but also it's possible to predict what they look like using a few simple rules just by hand, which is, I guess, good if you're ever stuck without a computer and need to stabilize an unstable system or something like this. But also it's good to understand why a root locus plot looks like what it does. So that's what we're going to look at now. And this, I think, will make more sense when we go through an example. So once again, it's sort of a one-liner in Python or MATLAB. We have an inbuilt rlocus command. And it will either output the plot itself automatically if you have plot equals true. I think in Python in particular, it's kind of nice to do things a little bit more manually, so at the expense of having more lines of code. But basically what I'm showing here are the root locus plots for proportional control for my two systems. So again, these are systems with the same A matrix, but different B and C matrix pairs. And so we see for system 1, remember this is the system that we weren't able to control, or that was still unstable when we used our simple k equals 1 proportional feedback. We see that the eigenvalues, or the eigenvalues are along these blue lines, which we observe never cross into the left half plane. So that's consistent. Conversely, sorry, this should be system 2, not system 1, but I can change that. We see here that as our controller gain changes, our poles, which originally were at these red crosses, move towards the left half plane. Again, consistent with what we had found empirically. Okay. So now the question is, do we understand or can we predict why these plots look like this? And that's what I'm going to do next. So it turns out that root locus plots can be constructed or approximated using a few simple rules. So to start with, root locus always starts at the open loop poles, or the poles of G of S, which in our case for proportional control is just the open loop poles of our system. So that is why these scales are different, but we start, or one end of our root locus, which corresponds to k equals 0, is at these open loop poles. Secondly, a point on the real axis is included in the root locus if there's an odd total number of poles and zeros to the right of it. And here's where the fact that our system 2 has a 0, but our system 1 does not, starts to have an impact. Because the total number of poles and zeros for our system 2 is 3, which is odd. So what that means is that everywhere to the left of, to the left of all three of these guys is going to be included in the root locus. So that means there is a k value such that any point on this blue-colored portion of the real axis is an eigenvalue for our system. And actually, it goes all the way up to where this 0 is, because, these two poles are both at the same location. So every point to the left of this 0 has either 1 or 3 total poles and zeros to the right of it. So it doesn't particularly matter whether this 0 is to the left or the right of these poles. And then lastly, as our controller gain goes to infinity, the branches of the root locus which go to infinity asymptote to straight lines that are given whose angle with the positive real axis is going to be given by this. And it turns out that the number of these lines that go to infinity is given by the relative degree, which is the number of poles minus the number of zeros of our transfer function. So again, the relative degree of system 1 is 2, because we have 2 poles and no zeros, while the relative degree of system 2 is 1, because we have 2 poles and 1 zero. So that means that system 1 has 2 lines going to infinity, and if we use this equation, we find that those lines are at pi on 2 and 3 pi on 2, whereas here we only have 1 line, which we find is at negative pi, which is consistent with our finding regarding the real axis, or this rule 2. So the point that I'm making here is that even if we didn't go through the math explicitly, by sort of using these rules, we could infer that proportional control is never going to stabilize, or proportional control, is never going to stabilize system 1, but is able to stabilize system 2. And there are more complex rules that can help you out, which can be particularly important if you have more complex systems with lots of poles and zeros that might be close to each other and so forth. Okay, so I wanted to introduce, this is sort of one method to study the dynamics of linear systems, or particularly the response under control. It's one of several methods. I'll mention a few more later on. We're not going to have time to cover all of them because, again, this is sort of an abbreviated course in controls. But the idea here is that we can use these tools to build up or validate our intuition or our empirical findings regarding what works and what doesn't. Okay. So now we're going to change pace a little bit. So rather than taking just our output y as the input to our controller, we can also have cases where we actually have access to the full state, or perhaps an estimate of the full state. And I'll talk a little bit more about that later on. So that changes the topology of our control diagram a little bit, but more or less it's the same. It's just that we have a vector now going directly out of this state propagation equation through our controller and then to define our control law and thus our input to this system. And then our output block can be considered separately. And in this case, as before, we have modified closed-loop dynamics. The only difference is that we don't have a C term here now because K acts directly on X. So why am I introducing this? Well, I guess it should, in theory, allow us to do better because we know the full state rather than just the output, which might be, in this case, and is in this case, a limited number of states. But it also allows us to develop other tools. So for example, we could ask, well, maybe we're going about this the wrong way. Rather than designing a controller and then seeing what it does, or maybe using some tools to design a controller but then needing to test it anyway, could we start the other way around and ask, can we explicitly say, I want to have closed-loop poles at these particular locations? Maybe because that will stabilize our system. Maybe it also has other favorable dynamics in terms of how quickly we'll drive our system to zero. And use that explicitly to design a controller. And the answer is yes, provided that our system is what we call controllable, which means that we're sort of, through our control law, able to drive the system to whatever state we desire. But that controllability can be tested through looking at the rank of the controllability matrix, which is what you get if you stack together your input matrix, or vector B, with successive powers of A. And so it turns out that computing the rank of this matrix will determine whether your system is controllable. Which means, at the end of the day, one, as I said before, it means you can drive the system to whatever state you want, but also you can design a controller that will put poles wherever you want them. And so I won't say too much about the theory as to why this is the case, but we can see for our simple system in practice whether or not we can do this. Okay, so now we're on to looking at full state feedback. And as I said before, our first step is to verify that our system is controllable. So once again, I don't have to form the controllability matrix by hand. There's a nice shortcut, which is exactly the same as what's in MATLAB. And then I can just compute the rank of that. And my system has two states. The rank of my controllability matrix is 2, so we're good. And this is system 2. This is system 1. I could also look at system 2. And it turns out that's also controllable. And again, I only need the A and the B matrices to compute this. So I claimed that means that I should be able to put poles wherever I want them. So we can try this. And so this is called pole placement, which is one form of full state feedback that we can implement. So how do we do this? Well, I start off saying I want my closed loop poles to be, in this case, at -1 and -2. So in the left half plane, so I have a stable system. I can design my full state feedback law, which now is going to be a matrix that maps between my system state and my input. So it's going to be a 1/2 matrix. And then, so I can do this. I get my controller gains. So this is what I multiply each of my state components with to form my input. And then I can verify, when I look at the closed loop poles, they're exactly where I asked them to be. So this is nice. We now have full authority to put poles wherever we want. So if I wanted one of these to be at -10 rather than -1, then my controller gains increase, but I can get the desired closed loop performance. Are there any questions at this point? Okay. But this still seems sort of arbitrary. Like, it's nice that we can do this, but we're kind of relying upon some sort of intuition or knowledge of what we want our closed loop dynamics to be to decide where we want to put our poles. So that sort of motivates the question, can we define a controller that is in some sense optimal? So what might we mean by optimal? Well, perhaps we want a controller that's very good at making the output of our system whatever we want it to be. So that is tracking a desired reference signal, which what we've looked at so far just means driving our output to 0. Well, at the same time, not wanting to exert too much energy. Or mathematically, we have a cost function where we sort of have a penalty on non-zero states of our system and a penalty on how much energy our controller needs to exert. And so some of these methods actually are sort of a simplified or special cases of some of the ideas that Professor Schmidt was talking about last lecture, where we have an optimization problem that we wish to solve, which for linear systems is relatively easy to do. So by defining these positive definite weighting matrices that define sort of the relative importance of sending our state or components of our state to zero versus how much energy we exert between different components of our control, we can seek to specify a controller that is, at least in this sense, optimal. Okay, so let's have a go at doing that. And again, I won't go into the details too much about how this is computed. It turns out for a linear system, you end up with an algebraic Riccati equation, which is relatively easy for a computer to solve at least, and which again, in MATLAB or Python, there are inbuilt packages that do all this under the hood for you. And the nice thing about this form of control is that as well as being optimal, we also have, in some sense, a guarantee of robustness, which comes in the form of guaranteed stability margins, which I'm not going to go into too much in this lecture, but it's sort of a nice added bonus for LQR control with full state feedback. So once again, let's implement this in practice. So again, the choices that I have now are my R and Q matrices. So again, Q specifies how much I want to penalize not being at the state that I want to be at. And R penalizes the effort that my controller has to exert. So let's try three different examples of R. R is a scalar here because I only have a single input to my system. And we'll just take Q to be the identity. And really what matters here is the ratio between the sizes of Q and R. Okay, so again, my controller is given by this K LQR. And actually, if I wanted to look at I'll say LQR equals 100. I just realized it might be useful to actually see what the controller is outputting. R equals 1, R equals 0.1. This should be K LQR1, LQR2, and LQR3. So I can run this. I get my three different controller gains. And these actually make sense if you think about it. So when R is really big, I'm penalizing the effort that my controller has to exert a lot more. And so I end up with relatively low controller gains. Conversely, when my R is small, I allow my controller to have a lot more freedom to use up a lot of energy, and so I get comparatively larger gains. Then what I can also look at is how these controllers move my eigenvalues. So the black crosses here are the open loop poles of my system, of the uncontrolled case. For R equals 100, that's where I have very small controller gains. We stabilize the system, which we're guaranteed to do, but we don't move the eigenvalues very much at all. So this is kind of like the low effort controller, the sort of the student that just wants to pass and does minimal effort in order to get the one outcome that they need to do, which is to stabilize the system. Whereas if we allow our controller to be more aggressive, then we move the eigenvalues further into the left half plane, and presumably drive our system to the desired state more quickly, which we can test. So what I can do is generate my closed loop systems with my various LQR controllers with different levels of aggressiveness, shall we say. And then do our same trick before, where we'll run our system and then at a certain time turn on our closed loop control and see how our controllers perform. And this is the response that we get. So we see, again, as we expect, all of our controllers stabilize our system. But the one which only shifted the eigenvalues a little bit still sort of has this ringing at about the same frequency as our unstable system. Whereas the more aggressive controllers drive our response to 0 more quickly. Now, which one is better? Again, probably depends on how much authority your controller might have in practice, or how much energy you want to exert driving your system to whatever you want it to go to. Okay, and actually, no, I won't do that. So, what this means, so we've kind of introduced a range of ways in which you can design controllers to stabilize linear systems. For all of them, there are some parameters that you need to define. So in some cases, you directly define parameters that define the dynamics of your controller. So that was the proportional or PID control. You can directly define what you want the eigenvalues of your closed loop system to be if you have full state feedback. And so that was pole placement, where we used the place command. Or we can define an optimal controller where we need to specify these Q and R matrices. So depending on what is the more convenient user input or how much you know about your system, there are numerous tools available here. So there are many, many more methods that we could talk about, which I'll mention briefly, but not do any examples of. So one thing that I'm not going to have time to talk about is looking at other ways to analyze linear systems. So we looked at the root locus plot, which is one of several tools that can be used to understand dynamics, predict stability, and design controllers. So you can also look at Bode plots, at Nyquist plots, and then define metrics related to how close to being unstable your, say, closed loop system is. Another thing that I haven't talked about, but that we can also do, is we can still utilize some of these full state feedback methodologies, even if we don't directly know the full state, by using an estimator. So such as using a Kalman filter. We can use the estimated state as a proxy for the true state in order to apply full state feedback methods. So for example, one can do LQG control, or linear quadratic Gaussian control, which combines a Kalman filter with an LQR controller. And the nice thing about this is that if you design both of them separately to be stable, then your combined system will be stable. Though there are some issues in terms of not getting the same robustness properties that you get for, say, a full state LQR controller. I will mention that these things are easy to do in MATLAB. In Python, it's a little bit trickier. So the Python control systems toolbox at some point has or doesn't have full functionality, in the sense that you can't just type in LQG. You kind of have to build things up by hand a little bit, but it's still relatively, or not too tricky to implement these sorts of things. And then I haven't really talked about several other methods that we can look at that either still are in the realm of linear control. So we can also look at robust control, modern control methods that are designed to give you, say, a specified closed loop specified closed-loop dynamics while also ensuring that your system is going to be robust to disturbances or uncertainties, which could include nonlinear effects, for example. And then there are other variants which can be particularly useful if, say, you have a nonlinear system that doesn't have one sort of global linearization that's always going to work. So, for example, you can look at finite time horizon model predictive control, which has a similar setup to some of these other methods, particularly LQR, but again can be beneficial to use in applications where you don't have a perfect linear system that's going to remain the same linear system for asymptotically long times. The point that I wanted to make, or one additional point that I wanted to make, is that even though a lot of these tools are simple, and a lot of you probably have come across them before in an undergraduate or a graduate controls course, that a lot of these tools can actually be implemented in practice. I might talk a little bit more about where they can't, but for example, if you look at canonical fluid flows, then there are several examples in almost every canonical fluid flow where you could see the successful implementation of linear control methods to control a nonlinear system. So, for example, we can look at controlling or delaying the transition to turbulence in a boundary layer. And really, what I'm trying to show here is basically the same plots that I was looking at for my simple system, but applied to a more complicated or real flow. So here we have, this is from Belson et al. We're looking at controlling a transition in a boundary layer, and we find that with control, we're able to drive our system closer to zero. And this is with just simple PI feedback. So nothing more complicated than a proportional gain plus an integral gain. Of course, you have choices regarding where you put your sensors and actuators, which again is sort of beyond the scope of the example that I looked at. But by modeling the system in the right way, you can actually utilize some of these tools in practice. So one can also look at flow over cavities. So this was some work by Barbagallo et al., I think including Peter Schmidt and Denny Sipp, where, again, you have an uncontrolled system, which is this red line. When you turn on your feedback controller, you kind of can control this instability. And I believe this was using LQG control. So again, something similar to the optimal control that we talked about. One can also look at control of bluff bodies. So again, there's several works on this of which these are only some, and this is a plot from Illingworth where for control, I think we use blowing and suction on the cylinder, and we're measuring, and the authors are measuring at certain locations in the wake and managing to stabilize flow over a cylinder at a Reynolds number of 100. And again, I think this is using H-infinity control, so it's one of those robust loop shaping variants, but still just using linear modeling and control methodologies. And then lastly, if we look at a highly nonlinear system, so wall-bounded turbulence, then again, relatively simple linear control, modulo certain technicalities, can be shown to effectively manipulate your system. So this is classic opposition control. So we sense somewhere in the flow and then actuate sort of in the opposite direction. So really, this is just proportional control with k equals 1, most simply. And it was shown, I guess, first explored in the 90s by Choi et al. And you can show you can actually reduce the required pressure gradient to drive your system using these simple feedback control laws, which here is really sort of manipulating the dynamics close to your boundary. Now, of course, there are a lot of caveats with when linear control works. So you need to have control authority. You need to have a good model for your system, and so forth. But the point that I wanted to make is that, at least as a starting point, it can actually be used in practice. And over the last several decades, it has been successfully used in a range of applications. So the last example that I wanted to show was an example that I did actually with Steve and Clancy early in my PhD, where we are controlling the lift on this airfoil, where now our desired lift is some arbitrarily varying function, and so we design a feedback controller that sort of tells our airfoil how to move in order to obtain this desired lift coefficient. So again, it's a relatively simple system because it's a low Reynolds number, and we're actually directly measuring the thing that we're trying to control. But again, it's a highly nonlinear system because we're going over quite a large range of angles of attack, but linear control works. So, and that basically wraps up the material that I have. So I'm happy to take any other questions or comments at this point.
Thank you very much, Professor Dalton, for this excellent review. Questions? Okay, maybe I have one very quick. When you use this kind of methods and you base yourself on a system identification step, let's say, to get your system, what will be your advice concerning the tuning of these parameters, such as your LQR, so your Q and your R, when it comes to the sensitivity of your identification step? So let's say that your identified system is not exactly the good one. What can go wrong if you decide to actuate with an LQR?
Yeah, so that's a good question. So LQR, sort of as I mentioned, does have some guaranteed stability margins, so that's good. But I imagine that, for example, if your controller is too aggressive, then maybe you can excite dynamics that are not modeled in the model that you've gotten for your system. And where that could happen is if, in doing feedback, if let's say you identify a model using an uncontrolled system, now all of a sudden you're applying some control to it, you're going to be exciting dynamics that are not modeled at all. And so that could be a problem, which I kind of skirted around here by, well, obviously using a simple example where I'm assuming that I'm restricted to this two-dimensional subspace, which doesn't happen in practice. So I guess possibly what you would want to do is, in the system identification step, use data where you're actually actuating your system in some way. And that might not be guaranteed to work, but at least you want to do your system identification on data which is representative of what you're going to get when you implement your control. Now, there might be other issues as well in terms of at what point you want to sort of truncate your system, but that's perhaps one aspect that is a complication that needs to be considered.
Thank you. Other questions? Okay, then I have another one then. When you do your linearization, you decide over a certain interval of time within which you are going to build your system and then act. In case your problem is non-linear, maybe one obvious solution, say, might be to try to reduce your time, to try to linearize it in smaller step. And how helpful could that be if you try to make like piecewise linearization all the time?
Yeah, so one could do something like that. And then I guess when you're designing a controller, that's where something like model predictive control can help, where you're trying to optimize just over a finite time horizon. So if you at least know if you know some linearized dynamics that are relatively accurate, at least locally within the region of state space that you're in, then probably you have a better hope for that sort of more tuned control strategy to that particular region of space that you're in working. So I guess that's one comment that I would have there. Yeah.
Thank you. Other questions? Well, it seems it was really clear then. I think then we can go for lunch, and we come back as planned, I would say. So we have a slightly shorter lunch break. What do you think? Is it okay? I take it as a yes. Thanks again to Professor Dawson.
Okay, good. Yeah? You can hear?
Okay, so welcome back to this second session on dynamical system. The next two lectures will be given by Professor Brunton. The first one would be on nonlinear dynamical system to complete the pictures that we have seen today. And then we will move to system identification. Okay, so the floor is yours, Professor.
All right, wonderful. Hello, everybody. I'm Steve Brunton. I'm really, really happy to be here and to tell you about one of my passions, which is nonlinear dynamical systems. So can everybody hear me okay in the back? Yeah, good. So how many of you also love dynamical systems? Good. How many of you aren't sure yet? All right, so I've got 1 hour to convince you the dynamical systems are the coolest. And really, I will say that dynamical systems, nonlinear systems, are why most of us are here. So fluid mechanics are one of the original hard dynamical systems. And so this could be an entire course. This could be a year-long course. I'm going to condense down all kinds of interesting stuff into approximately 1 hour. Okay, so this is, pretty shallow. And if you have any questions at all, at any point, please interrupt me. Okay, just like either shout or raise your hand if you have any questions, okay? How many of you have taken a class on dynamical systems? How many have not? It's okay, perfect, good. So I'm gonna talk to both of you. Okay, I'm gonna start off and I have a couple of pieces, and so anything you're interested in, we'll just talk more about. Okay, so dynamical systems, I was thinking about this. Really, any system that evolves or changes in time is a dynamical system. So I always joke with my mechanical engineers that we like time derivatives, DDTs, otherwise we would be civil engineers. Okay, so everything we care about evolves in time, all right? And I'm just gonna give you some examples. I love roller coasters. It was actually hard to find a movie of a roller coaster, but the way I think about the world, dynamical systems are movies. They're not still images, they're movies. They're frames that are evolving according to some physics or some dynamical systems law. We're all here because of fluid flows, in particular unsteady fluid flows, flows that vary in time, okay, and in space. Very high dimensional, nonlinear, multi-scale dynamical systems. In fact, I want to say that again. So the dynamical systems that bring us here today are nonlinear, multi-scale, high-dimensional, okay? Those are really key challenges that we face every day in fluid mechanics. And partly what is interesting about this to me as an applied mathematician is that the same complexity that we have in fluids, we also have in neuroscience. So your brain is a collection of maybe 100 billion neurons that have some very specific connections. They're constantly firing and passing information in time and in space. This is a very high-dimensional, nonlinear, multi-scale dynamical system. Okay, what do I mean by multi-scale? What I mean by multi-scale is that you have your whole brain. Your brain is broken up into regions. Those regions are broken up into smaller regions, and eventually you get down to the cellular level and even the molecular level. And all of those dynamics actually do, in fact, matter to how you think and perceive the world. It's also multi-scale in time. You are listening to the words I'm saying right now over seconds. You're thinking about what you had for lunch, that's minutes. Okay, you're thinking about what you're going to be doing on Saturday. Right? And that, let alone, you're also thinking about months, you're planning years ahead, you have a continuity of self over your entire lifetime. That's extremely multi-scale. You care about fractions of seconds, you care about decades, okay? And our fluid flow is similarly very, very multi-scale in space and time. So that's what I mean by multi-scale, is that you care about big scales and you care about little scales, both in space and in time. And that makes it very challenging. It makes it expensive to simulate and to analyze these multi-scale systems. Okay? So other interesting multi-scale systems I think about a lot are disease modeling systems. So I guess, yeah, a little bit timely, Bernd. is this is an image I got from Josh Proctor, a collaborator of mine at the Institute for Disease Modeling. So if you think about the spread of a disease across a continent, you can think about this in many, many different ways as a complex, high-dimensional, multi-scale, nonlinear dynamical system. So one way is what is called agent-based modeling, where each human individual is an agent. So maybe there are, about 10 billion states in this system. And then there is a very, very sparse network that's evolving in time of how we're interacting. So for example, us 200 right now are connections in this graph. Okay, and when we go home, that's going to be connecting to other nodes in the graph. And so you have this time-varying spread of information across this network. And each node is a nonlinear dynamical system. You have an immune system. You have a behavioral pattern. It's stochastic. It's nonlinear. Okay, very, very complicated. So when I say high dimensional in fluids, does everyone know what I mean? I guess what I mean is that if I wanted to simulate that fluid, I would have to chop up my domain into 1 million or 1 billion grid cells, and then I would be solving 1 million or 1 billion order differential equation. Okay, and that's hard, that's expensive. Okay. In addition, other dynamical systems that are high-dimensional, nonlinear, multi-scale are the climate, the atmosphere, ocean dynamics. This is one of my favorite visualizations Philip Dutoit made in his PhD at Caltech with Jerry Marsden. So these are the Lagrangian coherent structure mixing patterns for the entire ocean. This is actually a movie, but each frame took a supercomputer like weeks to compute. Okay, so again, it's very expensive sometimes to compute. And I'll tell you more about what this visualization means later. Okay. Other dynamical systems that are not as complex or high-dimensional, multi-scale. I mean, this is pretty complex if you think about the rocket and the engine and the combustion, but I'm mostly just thinking about the actual landing of this SpaceX rocket, which is essentially a big inverted pendulum, right? This is a pendulum that's inverted, and they're trying to keep it inverted as they slowly land this back on the launch pad. So this is a classical nonlinear dynamical system that we want to control. Okay, that's one of our chief objectives, is not just to understand systems or to simulate them, but to modify their behavior and control them. So if there was an active feedback control, this would just tip over and crash. Okay? Similar to how I'm walking, actually. I'm an inverted pendulum too. Very unstable. And I think to some extent, a lot of our understanding of physics, classical physics, modern physics, has come from watching the stars. And I actually think this is kind of an interesting image, because if you look at this, you're thinking to yourself, this is just an image. And on our time scales, we don't really see these things moving very much. We see planets moving. We see the stars rotate in our frame of reference. But these, galaxies aren't moving on the time scale of a human life until you look at whether or not they're red-shifted or blue-shifted. And then you can actually see that there's a tremendous amount of motion in this dynamical system. Okay? So a lot of our understanding and appreciation of science in general has come from astronomy, which is, again, I mean, if you think about it, extremely multi-scale in space and in time. Okay, so I'm harping on some points here. Obviously, I care about things that are nonlinear, high-dimensional, multi-scale. Okay, good. Is everyone motivated? All right. Everything you care about is a dynamical system. If you have a dog at home, it's a dynamical system. Okay, so I want to talk about the anatomy of a dynamical system. I think of this as our model for reality. So reality is complicated. We can only model things about it. And we want to model reality at different levels of fidelity. So something I'll talk about in the next lecture on system identification is this idea that you get to, in some sense, choose F to model what you observe, okay, your measurements of reality. And there's always this dual balance between complexity of your model. Do I model every detail of the system? Do I model the air molecules in this room? Or do I model the bulk properties, the temperature and the pressure, okay? And so there's always this balance between accuracy and complexity. And what I would love to find is a model that's somewhere in the middle, okay? So I'm just going to walk through this. X dot equals, how many of you have seen this before? How many have not ever seen something like this? It's okay, good. Just going to go through really briefly. When I write down a dynamical system like this, I'm always thinking about this in terms of the state of the system. The state is the minimal vector of information that I need to describe my system at right now. Okay, so think about a pendulum. So you know that a pendulum has an angle theta, but if I'd only give you theta, do you have enough information to simulate the pendulum forward? No, because if I have this angle theta, I could be swinging through it this way or this way. I need a velocity, theta dot. Okay, so theta, theta dot would be the minimal state of that pendulum system. Okay, so that's what X is a vector of information that you need. F is essentially what we call the dynamics. It is a set of equations or constraints on how X must evolve in time. So that is your system of ordinary differential equations. Okay? Sometimes this comes from Newton's second law. It can come from conservation of momentum, the Navier-Stokes equation, lots of ways of getting F. In the disease modeling, you could just write down a model, okay, and see if it's good. Now, I'm going to give myself the option of having my dynamics evolve in time. Oftentimes, we're going to have F be a constant function of X. Sometimes F will change with time. Okay, so some examples of that. The climate. The climate dynamical system today is different than it was 50 years ago. The system is being actively forced. It's changing in time. Okay, so things are evolving in time. The dynamics themselves are evolving in time. The economy and finance is a time-varying dynamical system. Okay, the rules today are different than the rules 10 years ago. U is our actuation or our control. So oftentimes, and sometimes we'll get rid of this, sometimes we'll keep this, but in a lot of systems of interest, I have some control knobs that I get to play with to try to manipulate the behavior of my system. Okay? And then beta are going to be all of my parameters of the system. These are the things that I don't necessarily have control over, but they do determine the qualitative behavior of the dynamics, and I'm assuming that they're more or less fixed in time. So it's just a set of parameters that define my system. So like temperature in this room, for example. Okay? Good. Any questions? Okay. So I talked about having access to this state, which is somehow the full state of my system. Now, in my fluid equations, that would be, the velocity and pressure at every single grid cell. So that might be millions or billions of dimensional X. Oftentimes, I don't actually have access to X in the real world. When I'm flying an airplane, I don't actually know exactly what the flow field over my wing is. I only have a few pressure measurements, a few measurements of my system. And so in most cases, I actually only have access to these measurements Y. Okay? So I want to walk you through what are some of the key challenges in nonlinear dynamical systems today in the modern era. So we've been working with dynamical systems for a really long time. Isaac Newton wrote down dynamical systems, nonlinear systems. The modern perspective on dynamical systems is only about 100 years old, starting with Poincaré. Okay, and I'm going to talk about what are the key challenges, maybe in the last 10 or 20 years, that are still problems now. Okay, and I should point out, when I say nonlinear, does everyone know what I mean? Yes? Okay. If I had a linear dynamical system, Bernd knows what I mean. It would be x dot equals a matrix A times x. And we know how to solve matrix systems of equations, right? It's e to the exponentiate A times time. Okay, that would be the solution at forward time. And what linearity means is that if I have two solutions, when I add them, their sum is also a solution. That is not true for nonlinear systems. Superposition doesn't hold. Okay? That's the key takeaway of what nonlinear means. And it means that all of our nice fancy tools go out the window. Okay, so challenges. The first challenge I'm going to point out is that oftentimes F is not known. We don't have equations for your brain. We don't have equations, or we can't agree on equations for the climate. Okay? We don't know what the equations for the coronavirus are. We don't know. So we don't know the dynamics for almost all of the systems we care about. Even the systems we do care about, like the Navier-Stokes equations, we have a beautiful set of equations that very, very accurately describes incompressible fluid flows, but they are too complex to use for everyday design, optimization, and control. Like, try to simulate Navier-Stokes in real time for a scramjet, right? We can't do it. That's why we don't have good scramjets, because we can't do, real-time model-based control. If we could, we would have them. That's oversimplification. That's not true. But so even when we do know F, we need reduced order models that capture the dominant coherent structures, the patterns, the things that actually matter to our engineering objective. And so we need to be able to build these models F from data. So that's probably the key challenge. And it's not talked about that often. We usually assume we have a model F when we start our dynamical systems class. But the systems I care about, I don't have F. Okay? What are some other challenges? Actually, I want you to tell me. What are some challenges of dynamical systems? What do you wrestle with? Noisy measurements. I know you wrestle with that every day. What else? So noisy measurements. Isabel? I didn't hear the first word. Yeah, so like getting enough data to characterize the system. Bernd? Okay, finite time horizon. How?
Neighboring, strong causality is not obeyed. So neighboring trajectory can end up completely different ones.
So strong dependence on initial conditions, chaos, uncertainty, amplifying in time. Okay. So does everyone get uncertainty amplifying in time? Like I'm an inverted pendulum. If I go a little to the left, I go a lot to the left. If I go a little to the right, I go a lot to the right. That amplifies in time. Okay. So I've already talked about nonlinearity. Nonlinearity is a huge one. That is what keeps us all in business. Okay, so seriously, you have job security, no matter how young you are, because of nonlinearity. That's why we're all here. If our world was linear, we would go home right now. Okay? I've already talked about high dimensionality. The systems we care about and we're talking about are massively high dimensional and multi-scale. Yeah, good. Chaotic, this is what Bernd talked about. It is, if I have a simulation and I just breathe on that simulation the wrong way, it diverges into a different solution. That's what chaos means. A big one, a really, really big one, is having hidden variables, latent variables that you didn't realize you should have been measuring. And that goes to Isabel's point of available data. Oftentimes, we do our best job designing an experiment. We think we measure everything and control everything. And it turns out that there were some variables we just didn't account for. Okay? Or maybe I only have access to certain measurements and I didn't measure the full state X. That's a huge one. Okay? Noise and disturbances. This equation was just wrong until I add this plus disturbance. And this equation always has measurement noise. And we always assume that they're white Gaussian, but that's almost never true. Okay? Almost never true. And then I think really critically, there is uncertainty in every single piece of this equation. Okay? There is uncertainty in the structure of my ordinary differential equation. There's uncertainty in my measurement of x or of y. There's uncertainty in the parameters. Maybe my temperature is only good up to plus or minus 0.1 degrees Celsius, because we're here, or Fahrenheit. And maybe that makes a huge difference on your solution. Okay, so understanding and quantifying uncertainty is one of the biggest challenges we have today in dynamical systems. Okay, now something I want to point out, because tomorrow you're going to hear all about machine learning, right? That's why we're here to some extent. And I'm going to tell you about my perspective on machine learning and machine learning to solve some of these problems in dynamical systems and to solve some of these problems in fluid dynamics. And what I want to point out is that almost every single challenge that I've listed here, and they're not problems, right, because that would be negative, they're challenges, they're opportunities. I'm not kidding, they're opportunities for you to make your name in your career. These are all opportunities, okay? If someone tells you something is hard and can't be done, go work on it. All of these are optimization problems. In fact, almost every problem in fluid mechanics and dynamical systems and control theory can be written as an optimization problem. And the perspective I'm going to take tomorrow is that essentially machine learning is just optimization based on data. Okay, so these are all things that we can use and leverage modern tools for. Okay? Would anyone like to ask any questions? Is everyone feeling good about this? Okay, good. So why do we actually want this model in the first place? Of course, we want to be able to predict the future, right? We want to be able to simulate our, turbulent flow or our combustion or whatever we're doing and see what it does, how it behaves, does it blow up, right? I want to know. And sometimes actually our dynamical systems, so in chaotic systems and turbulent systems, oftentimes I don't care so much about one individual trajectory. I care about kind of an average trajectory or an ensemble of trajectory, the standard deviation of what my trajectories might do. So I might want a statistical prediction of the future given some uncertainty. Okay, that's key. I want to use this model oftentimes for design or optimization. So if you think about Formula One or rocket engines or yachts, you're going to use these models to accelerate some kind of a design or optimization process. Actually, I think the rocket engine I showed for SpaceX is a really good example. During the space race, when NASA was building rockets, they blew up like 1,000 J-1 rockets, testing the different geometries and combustion chambers and ratio. I mean, it cost $1 trillion in modern dollars, okay? And they could do it because they had to do it, but we can't afford to do that now. I've talked to engineers at Blue Origin and SpaceX. They can't afford to test 1,000 rocket engines and have them all blow up on the launch pad. So they need better predictive capabilities, better predictive tools about if it will or will not blow up before they blow it up. I mean, it's a really simple distillation. But this could cost $1 trillion or not, depending on the quality of your model. Okay. I personally want to control everything, especially my dynamical system. So control is really important, right? You have your dog's a dynamical system, you tell your dog to sit, you want your dog to sit. Okay, so you're going to train, you're going to control your system, you're going to learn how it responds to your commands, and then you're going to change those commands to get the behavior you want. That requires a pretty good understanding of the system. Okay, it's like psychology. This is dynamical systems psychology, it's control theory. And at the end of the day, I want to actually understand my system. I don't just want this to be a predictive tool. So a lot of people in machine learning are going to tell you that they have a model of your system because they trained a big, deep neural network, a big black box, okay? And that may very well be useful for future prediction, optimization, and control. We also want to understand our systems, okay? And we want our models to be interpretable, meaning that this F is not so complex or so abstracted that I can't communicate to you what it does. Even the Navier-Stokes equations, which are very complex, I can tell you what they are in one sentence. It's conservation of momentum in a fluid. It's interpretable. It's also very generalizable. I can write down that I can learn that from one set of fluid experiments, and I write it down, and it applies to lots of other cases of fluids that I've never seen before. That's something you want in your models, trust me. Okay? Especially if you're going to do control with those models. Okay, good. That's my spiel. Those are the things I care about in dynamical systems. Those are the things I think that there are hundreds and hundreds of careers in the future on dynamical systems, especially in fluid mechanics. So now I'm just going to tell you all about dynamical systems and examples and fluids and just cool stuff. And again, please interrupt me. So this is a picture that I have adapted from kind of where I learned dynamical systems, which is Guckenheimer and Holmes' textbook, 1983. It's a really good book. Highly recommend it. And so I think about dynamical systems as an increasing progression of nonlinearity and complexity. Okay, so on the left we have linear systems, which we really kind of perfectly understand. Okay, spring mass systems, small amplitude pendula, periodic oscillators. We know every single thing about these systems. In the middle, what we have is kind of weakly nonlinear systems, where it's not as simple, but it's not chaotic. It's kind of deterministic behavior. And I'm going to tell you about this in a minute. Okay, how many of you have seen pictures like this? Phase portraits? Okay, good. And then kind of as you go down this progression of nonlinearity, you start getting into really chaotic systems. These are the ones Barrett was talking about, where if you just look at your initial condition the wrong way, it goes in a completely different direction. Okay, so these are our chaotic systems. I'm going to walk you through some of this progression. Have you learned about linearization in this lecture series? I know that Peter talked about this, the idea that you linearize your equations. I'm just going to walk you through. How many of you have not seen how to linearize a nonlinear system before? Everyone has. A little bit. I'm going to go fast then. So this pendulum is a good example of an actual nonlinear system that we can treat as a linear system in a lot of cases. Okay, so my pendulum, if I have a small amplitude motion, it just does a harmonic oscillator. Okay, that's linear. But if I increase the energy in my pendulum, it starts to act weird. The period changes. The period eventually becomes infinite as I go to the top, okay? And so it's a fundamentally nonlinear system, but it has two fixed points. Fixed points are states where the dynamics are equal to 0, okay? And this is really important in fluid mechanics. For example, your laminar boundary layer is often an unstable fixed point. It's a fixed point, but it's unstable. So if you breathe on it, it goes into turbulent boundary layer. Okay, so we're going to take our nonlinear system x dot equals f of x, and we're going to linearize it. We're going to zoom in near a region around some fixed point x bar where the dynamics are 0. And for the pendulum, the two fixed points are the obvious one where the pendulum is down. When the pendulum's down, it stays down. The other one is where the pendulum is up. And if you could perfectly build your experiment in the pendulum up condition, it would stay there. But it's unstable, obviously. Okay, so those are the two fixed points. And what we're going to do is we're going to say that our state x is some small perturbation delta x around our base state x bar. Okay, so our d delta x dt equation is equal to x dot because x bar is a constant, so d dt of x bar is 0. So x dot equals delta x dot. And that equals f of x plus delta x. And now what we're going to do is we're going to Taylor expand f of x bar plus delta x. This is pretty simple. We're assuming small delta x. And we get f of x bar, which we said was 0 because it's a fixed point, plus the Jacobian derivative of f with respect to x. This is a matrix of partial derivatives, okay, evaluated at your fixed point, times delta x, plus higher order terms that are order delta x squared or higher. So if I have small delta x, these are negligibly small. If I have a small zoom in around my fixed point, small angle approximation, I get a linear system given by this linearization. And this Jacobian, when I evaluate it at my fixed point, becomes a matrix A, and I get a linear system. Everyone okay with this? Good. And I can do that about multiple different fixed points. So that's good. I'm just going to go through this pretty quickly. Why linearization in the first place? So why do I want linear systems in the first place? Why do I take my nonlinear system and zoom into linear fixed points? Okay, because it's easier to solve, because if I can, I should, right? If I have a fixed point, I should go look at it. I would be a little bit more pessimistic. It's the only thing we can actually do with any reliability in nonlinear systems is zoom into fixed points and linearize them. We know everything about linear systems, so we go find fixed points and we linearize about them. And often we try to control our systems to stay near those linear fixed points. Yeah? We'll get there. Okay, so the basic idea, if I have this x dot equals ax it's easy for me to write down the solution at all future times. Okay, that's really, really important. I don't have to simulate some really complicated nonlinear stiff ODE with some fancy time stepper. I can just step this forward to any time in the future. Scott Dawson pointed this out also, that my control problem becomes like a one-line Python command. That's awesome. Okay, I love easy solutions. And you've all seen this before, but I think this is just really fun. When I have a linear system like this, it's easy to change coordinates. And this is, the reason I'm pointing this out is not because you don't know about changing coordinates in linear systems, but I want to take a big step back and point out that changes of coordinates is probably our most powerful tool in analyzing any system. That's how we discovered F equals ma, is by taking us out of the Earth-centric coordinate and putting us in the sun-centric coordinate. Took 100 years or more, okay? But then you got F equals ma out of it. Relativity is a coordinate transformation. The Fourier transform is a coordinate transformation that makes our lives simpler, okay? And this is the one that you're most familiar with, is this one here. So that's why I'm talking about this, because dynamical systems is also about finding coordinates where things are simple. So in linear systems, it's easy to change coordinates into some z coordinates. This T is just a matrix. I know how to multiply matrices. And in z coordinates, my z dot equations transform like this. Okay, so my A dynamics just become T inverse AT. That's what the dynamics look like in the z coordinates. And so I can do things like I can try to design my transformation T so that my z dynamics are diagonal and decoupled. Wouldn't that be nice? Because then I could solve the z1 equation, the z2 equation completely separately, okay? And in fact, if you write down that lambda equals T inverse AT, you obtain the eigenvalue equation. This is how you should think about eigenvalues and eigenvectors. They are literally the coordinates that turn your linear system into a diagonal system. That's why they're useful. That's one of the main reasons they're useful, okay? And that's how you can think of the Fourier transform too. It's the exact same thing, okay? And so now what you can do is you can write your state x at some future time t in this relatively simple formula that you've all seen before. But the reason I'm writing this up is to, again, bring it back to this idea of coordinate transformations. Eigenvectors of my matrix A define a coordinate system where my life becomes easier. That's what we want in all dynamical systems. And so the way I think about this equation, I break it down into these pieces. T inverse times x naught takes my initial condition and maps it into eigenvector coordinates. So now I'm in z naught. It's easy to advance my z dynamics because they're diagonal and decoupled. So I can advance z forward in time by just multiplying it times e to the diagonal matrix times t. And now I have z at some future time. I map back into my real spatial coordinates again through this eigenvector transform. So it's really nice interpretation of this in terms of coordinates. So linear systems are nice because it's easy for us to find good coordinates for them. Okay, and there's control analogs of this as well. Good. So I want to walk you through at least one example of linearizing something and doing a phase portrait. I think that's super important. This is the Duffing equation, and this is not the right order for the slide. My apologies. So this is the Duffing equation I had in the middle. So we've talked about linear systems. Now we're going to talk about how we can linearize around fixed points to build these phase portraits for nonlinear systems. This is the Duffing equation here. So x double dot equals x minus x cubed. And the way you can think about this is essentially a particle in a potential field, this v of x potential. So my force is minus gradient of my potential. This is just Newton's second law. And this curve here is my potential. And the way I think about this dynamical system is if I had a bead or a marble and I dropped it in this potential, it would roll around. Yeah? And if I started it right here, it would just roll back and forth. And if I started it here, it would roll back and forth. And if I started it here, it would go around, and so on and so forth. No friction. Okay? So when you have a system like this, you can suspend its variables into a higher dimensional system of lower order. This is a second order system, so now I wrote it as a system of two first order differential equations. So x dot equals velocity, velocity dot equals all this stuff on the right-hand side. And now if you look at this, the system has three fixed points. V always has to be 0, but now x can either be 0, +1, or -1. Okay, those are all of my fixed points. And now what I can do is I can compute that linearization of this fully nonlinear system through this Jacobian here. Does everyone know how to compute a Jacobian? Anyone want me to tell you? It's just like partial of f1 with respect to x, partial of f1 with respect to v, f2 with respect to x, f2 with respect to v. And I evaluate this at these three fixed points. And what I find is that the plus and -1 fixed points, sorry, I should tell you what the axes of this are. This is x, and this is v, and this is my phase portrait. So what this tells you is that this fixed point is stable. It has eigenvalues that just go, plus and minus I omega. So if I start here, I just go back and forth in x and v, which are circles here. If I look at this fixed point, the 0, 0 fixed point, then I have a saddle point. I have plus and minus real eigenvalues, so one of them stable and the other one's unstable. And this makes sense because if I started my marble right on that hill and I pushed it to the right, it's going to go to the right. That means if I start my marble right here and I push it to the right, it goes in this loop. And if I push it to the left, it goes on this loop. And then if I have slightly more energy, the colors here denote how much energy I have in my marble, then I'll just go around in phase portrait. So this is a really useful thing that we can do even in very high dimensional nonlinear systems like fluids. So the reason I'm showing you all of this is because we're going to look at this exact same type of picture for fluid systems in a little bit. Okay. Now, I absolutely love saddle points. I think that they are so cool and so important, and I'll tell you a lot more about them. Saddle points are essentially fixed points where some of the directions are stable and some of the directions are unstable. Okay, so in some directions I'm coming into the fixed point, and in other directions I'm fleeing away from the fixed point. That's what you see here. The green arrows are pointing in, the red arrows are pointing out. This is a nonlinear system defined by this equation here. And so essentially in this kind of a fixed point, you have stable and unstable manifolds. This red curve here is ironically called a stable manifold, even though it is fleeing away. Because if you think about it, this green set of arrows is pulling material in towards that red curve. Material is being glommed on to this red curve. It's adhering, it's attracting onto this red curve, and then being carried away. So things attract onto the stable manifold, and they repel away from this unstable manifold because this red curve is carrying stuff away from the green manifold. Okay? Good? And in general, I like to think about saddle points as being areas where uncertainty gets magnified. Okay? So for example, if I have these balls of uncertainty and I start them near this red curve, as I evolve the system further in time, those curves move out and out and out along those green directions. Okay? And what that means is that with a very small amount of input to my system of control, if I'm near a saddle, I can go really, really far in either direction. I get a lot of possible outputs for a very small change in my input. Okay? Good. I'll talk a little bit more about this. Yes?
So Maxwell already, he envisioned chaos as a separation by saddle points. He thought that the complex system must have a lot of saddle points, which act kind of as a flipper where you go right or left.
And I mean, to some extent, that is how our solar system works. That's how turbulence works. There's a lot of important saddle points, and I'm going to talk a lot more about these. Okay, I just wanted to point out this is what I'm talking about when I say a saddle. Okay, good. How many of you have heard of bifurcations? Good, perfect. So I'll go pretty briefly through this. Bifurcations basically means if I have some parameter in my system, this mu, sometimes I call it beta, I can get very, very different behavior as that parameter changes. So for example, in this case, I can write this system as x times mu minus x squared. How many fixed points are there in the system? It's a trick question. I hear some of you saying 3, some of you saying it depends, some of you, right? So if mu is negative, then there's only one real solution. I'm assuming that x is a real variable, okay? So if mu is negative, then there's only one solution, fixed point at x equals 0. But when mu becomes positive, 2 new fixed points appear at plus or minus square root of mu. So that alone is interesting, that depending on mu, I have a different number of fixed points. Okay, that's kind of what a bifurcation is. And so if I look at my Jacobian, my derivative of these dynamics with respect to x, I get mu minus 3x x bar. This is my fixed point squared. And so at these 3 fixed points, I get completely different dynamics. Okay, the x equals 0 fixed point and the x plus or minus root mu fixed points have the opposite sign dynamics. So one of them is stable, the other one is unstable. Okay, and that's what this bifurcation diagram, this pitchfork bifurcation, shows. The x-axis here is increasing mu, and the y-axis are essentially the fixed points x. So for negative mu, I only have one fixed point and it's stable. These blue arrows mean it's stable. I have one fixed point at x equals 0 for negative mu. And the instant mu becomes positive, that fixed point goes unstable. I think this should be, this is positive mu, so it's unstable. Okay, and immediately I get these 2 branches of solutions, these new fixed points that are themselves stable with these eigenvalues minus 2 mu. So this is what we mean by a bifurcation, is that as you vary your parameters, you get these drastic changes. So everything is the same, and then your whole world changes at a fixed value of mu. And this is something we need to worry about, right? Like the global food supply, populations, disease might have bifurcations where we're just merrily going along, and then at some point we crank something up too high and everything breaks. Okay, this would be a lot worse if this bent the other way. Okay, that's a different type of bifurcation. In fluids, we talk a lot about Hopf bifurcations. So I think you've already seen these before, and you're going to see more of these. So for example, in the fluid flow past a cylinder example, as you increase the flow velocity or the Reynolds number, you go through this Hopf bifurcation, where your steady flow pattern becomes unsteady at some critical Reynolds number, and then you get this periodic vortex shedding limit cycle. And if you had a sequence of Hopf bifurcations, you could eventually build a route to turbulence. Okay, that's the Ruel-Takens route to turbulence. And so this is the kind of normal form that you would get for a Hopf bifurcation in my 2 variables, x and y. Again, where mu is the thing that I'm increasing or decreasing to get this periodic behavior. Okay, and what I think is really interesting here is that if you write this in polar coordinates, and this is a good homework for you, you could probably do this on a napkin, is just write this in polar coordinates. You recover essentially your pitchfork bifurcation here. Okay, so I mean, and no wonder these look pretty similar. Okay, good. You can also have discrete time dynamical systems. So everything I've talked about so far is for continuous time, the time derivative of x equals f of x. But I could also have discrete time dynamical systems that step forward in time discretely, okay? And so this is one of my favorites, the logistic equation. So x at time step k plus 1 equals mu xk times 1 minus xk, okay? What would be some systems that are fundamentally discrete time in nature? I always think about my bunny population in Seattle. There are seasons. Okay, it's not exactly a continuous time system. There's, I have a bunny population in spring of 2019, and then I have a bunny population in spring of 2020 and 2021. And actually, that is what this equation is modeling, is essentially population dynamics. Okay. Anyway, you can also write down discrete time dynamical systems. That's something that we do a lot. Okay, would anyone like to ask any questions about anything I've talked about so far? Good. Okay, we're going to just build up complexity here. So I've talked about linear systems, weakly nonlinear systems where we linearize and look at phase portraits and stable and unstable manifolds and bifurcations. Now we're going to talk about chaotic dynamical systems. This is a video I made for my undergrad class to show them what chaos means to some extent. And there's a lot of different definitions of chaos. I think it's really fun and interesting. The definition that I think is most useful is a sensitive dependence on initial conditions. Okay, so if I started with two initial conditions that are very close to each other, and I integrate them through a chaotic system, so that cube started with really close initial conditions. And those initial conditions stay close to each other. This is the Lorentz system, by the way. They stay close to each other for a long time until eventually they don't. Then they start to spread and smear out on this attractor. And if I just showed you a picture at time now, you wouldn't know where all of these initial conditions came from. You wouldn't be able to tell which one was which one. Okay, so a small cube of uncertainty can amplify a lot in these chaotic systems. The Lorentz system is really interesting. It's essentially a three-state model to model convection, atmospheric convection. That's where Lorentz was trying to model. And he actually, you should go back and read this paper. My friend Jean-Christophe Loiseau convinced me to go back and actually look at this paper because Lorentz derives this using Galerkin projection onto hand-picked modes. So it's very relevant to what we're talking about today in this workshop. This is essentially a hand-tuned Galerkin model for Rayleigh-Benard convection. Okay? But this is what I mean by uncertainty growing in chaos. Okay? Another example I like to show in my class is this one here. So these are my double pendula that I built in my lab. I'm not an experimentalist, but this is about the best thing I can build. It's double pendula. Cardi, you'll see later, built some really nice ones. Okay, is this going to run again? So notice that I started them with the same initial condition. They were at that right angle initial condition. And they actually stayed together for a really long time. That was like my best initial condition I could get. I held my breath. It's pretty impressive. They stay together, and then they don't. Okay? Because small variations in the friction, the weight, all of those things eventually amplify into this kind of large growth over time. Okay? Now, what is the hallmark feature of a chaotic system and this increase in uncertainty in time? What's my favorite feature of a nonlinear dynamical system? Let's call, so an unstable direction. I would call it an unstable direction. You need some instability. Okay? Instability is one of our best friends for control. Fighter jets, the things we want to control the fastest, are designed to be unstable until you wrap control around them because they turn faster. A human walker, saddle points, right? I need saddle points for chaos. Because saddle points are going to have that unstable direction that I need to grow exponentially my uncertainty in forward time. Remember this picture here? This dynamical system exponentially grows uncertainty in the green direction. That exponentially grows in forward time. And that's exactly what chaos means, is this exponential growth of uncertainty in forward time. So somehow saddle points are important. The reason I study this pendulum system is because this has a very special type of saddle point called a rank 1 saddle. Okay, so I'm actually going to talk about this a little bit longer than I was planning on because pendula are super fun. So I can actually pretend that my arm is a double pendulum. Okay, this is the big pendulum, this is the little pendulum. Okay, and the system has how many fixed points? How many? Not 2? 4? 4 sounds good. So I could have down, down. Yeah, that's a fixed point. I could have down, I can't do this. Down, up. That's technically a fixed point. It's unstable, right? Because if I push this one, it's going to go. I could have up, down, also unstable, or I could have up, up. It's 4 fixed points, okay? Now, the down, down is stable, right? If I looked at the eigenvalues of this, I'd have like plus or minus I omega and plus or minus another I omega. It would just oscillate with 2 frequencies. But the down, up, and the up-down are what are called rank 1 saddles. They're only saddles in one of the directions. So I don't know which one I should use, but in this configuration, the big pendulum is stable. That has eigenvalues plus or minus I omega. But the little pendulum is unstable. It has eigenvalues plus or minus real numbers. It's a saddle point, okay? And these rank 1 saddle points are really, really, really important for efficient control and transport. As a human walker, I'm a multi-jointed pendulum, right? I've got my ankles, my knees, and my hips, so I'm like at least a 3-jointed pendulum. And that's a really good thing because I'm always constantly almost unstable. This is when I would normally wake up in Seattle, by the way. If you shot lidocaine into my ankles, I would fall over because I am a fundamentally unstable inverted pendulum until I actively control. And what's nice about that is that it means that I can very efficiently propel myself with almost no control input. All I have to do, right, I'm an unstable pendulum, I just go a little bit and I go a long way. I push myself a little bit off of equilibrium and the instability carries me almost for free in the direction I want to go in. Okay? It's an extremely good thing. Like, we are very efficient because we're unstable. Fighter jets are really, really easy to turn because they're unstable. And so these rank 1 saddles offer us the opportunity to control my system very effectively. So chaos, again, it's a challenge, but it's also an opportunity. Systems that are highly unstable can be manipulated easily. This is my favorite example of this. This is what Jerry Marsden and others were working on at Caltech in the late 90s that I think is super interesting, is using these saddle points for space mission design. Okay, so I'm going to walk you through this example. You have, let's say, the Sun and Jupiter. For all intents and purposes, those are the ones that matter in our solar system. Whether we like it or not, they're the big ones. And in the Sun-Jupiter system, there are 5 fixed points, these Lagrange points, L1, L2, L3, L4, L5. And I'm only going to talk about a couple. I'm only going to talk about L1 and L2. But L1 is clearly a saddle point. It's clearly unstable. It's the equal gravity point. Because if I was hanging out there at L1 just floating there, and you pushed me a little bit towards the sun, now I'm closer to the sun, and I'm going to accelerate towards the sun, right? And if you push me a little bit towards Jupiter, now Jupiter is more influential, I'm going to accelerate toward, it's an unstable saddle point. And it's one of these rank 1 saddle points. That's really interesting. It has 2 stable directions and 1 saddle direction. L2 is similarly a rank 1 saddle. And I don't know, it's a little hard to see these level sets here, but these level sets are essentially outlining what regions are permissible if you were an asteroid or a meteor traveling with a certain amount of energy. Okay? So if I have a low amount of energy, I would basically bounce off of that energy level set. And the only way I could get into the inner solar system is by going through L2, then around L1, and then into the inner solar system. And so to some extent, Jupiter is protecting us from space junk outside of Jupiter. It is providing these barriers, these energetic barriers, protecting the inner solar system. And so the only stuff that can come in or out with moderate energy is coming in and out through these saddle points. Those are the mediators. They're like the turning revolving doors for our solar system. And it's really interesting. During this time period, they discovered that some freakishly large number of asteroids in our near vicinity are in binary orbits with each other. which you would never expect, right? Space is so large and they are so rare, you would never expect asteroids to be orbiting each other. But something like 5 or 10% of our near Earth pairs are actually paired up. And the thought process is that because the only way they can come in is through these saddle points, that they had to have paired up as they entered the saddle points together. Very interesting. So it's essentially organizing the material in and out of the inner solar system. Yes?
Are you assuming that you have to be in the plane with the Sun, Earth, and Jupiter? What happens if something comes orthogonal?
Yeah, that's absolutely true, but most stuff is in the plane. Most of our space mass is in the plane. Really good point. You had me worried for a minute. So these saddle points are really interesting. They actually, if you wanted an efficient space mission, the best thing you could do is try to connect these saddle points, because then if I just push myself on one side, I go to one area. If I push myself on the other, I go to the other area. And so that's why people were looking at this. They could conceptualize this interplanetary transport network of these invariant manifold tubes connecting all of the different saddle points. So the Earth and the Moon have five Lagrange points. L1 and L2 are saddles. The Earth and the Sun have a bunch of fixed points. 2 of them, L1 and L2 are saddles. The Sun and Jupiter, the Sun and Mars, Jupiter and its moon. So there's all of these saddle points floating around in the solar system. And what you could potentially do is catch one of these highways and make an efficient, wait until it connects to the saddle point of another planet. And this is a real thing that you can do. So for example, in the US, this was called the Jupiter Icy Moon Orbiter, the JIMO mission, because we wanted to go check out all of the icy moons of Jupiter, because that'd be awesome, but we don't know what we're gonna find. So you're gonna orbit one moon, maybe it's super boring, okay? They don't do anything interesting on that moon. And so what you wanna do is adaptively change your mission to go hop to another moon. And if that one's really, really interesting, you might wanna stay there for 10 or 20 or 30 orbits. And then you wanna hop another tube to a different moon. And you wanna do this as efficiently as possible. You do it by using the saddle points in the system. We didn't pick it up in the US. I believe the European Space Agency did. Now it's called JUICY, which I think is a much better acronym, the JUICY mission. But it's all based on the saddle points. It's exactly the same conceptual dynamics that allows me to walk efficiently is now allowing space mission design to be efficiently designed. And we can also harness these in fluids, right? So for fluid flow control, saddle points are really, really important. Okay, these are the mediators where you can go, in very different directions with very little input. Okay, so when I was learning about space mission designs, chaotic dynamical systems, I always thought that if you increase the complexity and the dimensionality of the system, then you could only get chaotic, disordered mess. And that's not true. So there's this great video I want to show you. I hope this is playing, of all of these metronomes on a plank. Let me make sure it's playing. Okay, so someone's going to come and kick all these metronomes. So this is a high-dimensional, nonlinear dynamical system, bunch of oscillators. And what you're going to find, notice that the board is a little bit compliant. It can bend a little. You can do this at home. You can take 2 cans of soda and a wooden board, and you'll get enough coupling to do this. So this starts out in a very disordered state. They're all different phases. But very rapidly, you actually see that pattern is forming. In fact, it's almost happened. You can now feel that there are 2 basic groups. Okay, they've completely fallen into line. This is a little creepy. I turn the sound down. It's ominous to see everybody fall into line, okay? And just a small amount, a weak epsilon nonlinear coupling to these oscillators causes them to lock on with each other. Okay, this is a well-known phenomenon in high-dimensional oscillators, yes?
What the clockworkers have known already in 1600 to make their clock look much more accurately than they really were to put them on a wooden plate. And this way they would synchronize, and this way they would also at the same time for a long period of time.
Regardless of whether the time was right or wrong, they were all in agreement. And now, I mean, look at this. They are completely in lockstep. I'm going to fast forward just a little bit. Okay, I have no idea. Is there one that's out of phase? Yeah, this one's my hero. But this is a 3-minute video. So you can imagine what happens at the end of 3 minutes. Okay, so it's not all chaos and disorder and uncertainty. You can also have epsilon nonlinearities forcing synchronization and creating this order, kind of this emerging order in the system. I think someone had a question. Yeah.
On the slide that showed the pathways, there was a green ribbon of sorts. What is, out of sort of curiosity, what does that represent?
Sorry, in which figure? The planets?
One previous slide.
With the planets?
Yes.
Okay.
One after, yeah. So there is a green ribbon of some sorts that's being shown.
Oh, this is an artist rendition. It just looks better. I don't know. Like that would be your your trajectory on this thing. So this is an invariant manifold. It's an invariant tube. If you're inside, you can't get outside without spending energy. And then these green things would essentially be like a given trajectory on that tube over here. So it's just a trajectory, like a stylized trajectory. Yeah.
Just by curiosity, the YouTube with the metronomes, these had all the same frequency. Just started
Well, did they all have the same frequency? Can anything actually have the same frequency? I mean, yes, they're all metronomes, they're all the same frequency. But, in principle, there's uncertainty. They're not exactly the same frequency. And so this is a very, very well-studied system, actually. I mean, there's thousands and thousands of papers written on synchronization. And there are lots of well-known results about how strong the nonlinearity can be, what is the range of uncertainty and the frequencies that will cause them to lock on or not lock on. Actually, Benjamin Herman knows a lot more about this than I do, kind of these synchronization effects in coupled oscillator systems. Very, very well studied in lots and lots of different applications. So these metronomes do have the same frequencies, same natural frequencies, but you could detune them a little bit and still get the same behavior. Yeah, that's called like lock-on. Okay, any other questions? Yeah.
I actually didn't get why they synchronize.
Yeah, so it's a little funny, right? Like if I had, imagine that I had all of these clocks in different rooms in different cities across the country, right? So, this one's in Paris, and this one's in Berlin, and this one's in Seattle. They're not going to synchronize, right? There's no reason why they would synchronize. They synchronize because they're on this board, and this board is causing just a tiny amount of epsilon coupling so that if one is out of phase, it feels a restorative force trying to bring it into phase with the other ones. So how many of you have heard of the Millennium Bridge in London? That super cool, bridge over the Thames. The minute that they opened it up to people started walking on it. They noticed this tiny sway. But what do you do when you're on a bridge that sways? You hunker down a little and you brace against it. And so you have 10,000 people bracing against in order, and this is what happens. And they almost, they had to shut the bridge down. So, people have known this forever in the army, right? When you walk across a bridge, you break step, or else you break bridge. So, okay, good. So for the last 5 or 10 minutes, I'm just going to tell you some cool stuff about mixing, bring nonlinear dynamical systems into fluids a little. So this is kind of a neat video I made when I was in grad school. What you see here, this is basically a flat plate plunging up and down in a very viscous fluid. You can think of it like honey. Or maybe this is the wing of a fruit fly. Air is very viscous to a fruit fly. And you're creating these large recirculation zones. And you can see that after many, many periods of oscillation, you get this kind of chaotic mixing. You get a lot of mixing happening in the system. So if I started in two different places right next to each other, I might end up in very different regions of the flow after this pumping motion. So I'm going to tell you a little bit about these unsteady manifolds that I'm visualizing here. This is just a slide I made. I'm simulating the 2D incompressible Navier-Stokes equation with a code that Sam Tyra and Tim Colonius wrote, the immerse boundary projection code. You can download this. And you get these beautiful visualizations for, this is an airfoil plunging up and down. This is an airfoil pitching about its quarter chord. And these visualizations look a lot like the classic smoke visualization that you would see. And in fact, that is exactly what these are, is showing if I had dropped smoke, if I put a cigarette in this virtual wind tunnel, this is where the smoke would collect. Okay, but we're doing it mathematically in a simulation. Okay, so I'm going to tell you about what that is. This is called the finite time Lyapunov exponent field. And so Bernd said that you get chaos when you have a positive Lyapunov exponent. That means there's some unstable direction that's amplifying uncertainty. What a finite time Lyapunov exponent means is that over a finite time horizon, two initial conditions are massively separating almost exponentially in time. And so the finite time Lyapunov exponent essentially generalizes this idea of stable and unstable manifolds from my nonlinear dynamical system I showed you. Remember, I have this red stable manifold here, where material would attract onto that red stable manifold. That's exactly what these red curves are for time-varying fluid flows. So they're the unsteady analog of stable and unstable manifolds from dynamical systems. And I'll tell you how you compute these. So the way I think about this is, okay, Navier-Stokes equation is a dynamical system. I have some vector field u, my velocity field, and u sub t, my time derivative of u, equals some nonlinear function, diffusion, convection. If I dropped a particle in my fluid flow, it also sees a dynamical system. So the particle position is x. F is my fluid velocity field. And this really should be varying in time because my flow is unsteady. And what I'm going to do is I'm going to follow that particle through this vector field by integrating it along the flow field, getting this flow map. Okay, so I'm walking my white particles forward in time along the flow. In fact, that's actually what you're seeing here is I started with a grid of particles and I integrate them forward or backward in time. And what these red ridges are is if I took those white particles and I integrated them backward in time, the red ridges would be where two neighboring points separated the most in backward time. Kind of hard to compute, very easy to say. I literally drop a big grid of particles, I integrate them backward in time, and I look at which particles separated the most. That's what I color red. Okay? And what that means is that, so that's a movie in reverse. Then when I flow that movie forward, those points that had separated the most in backward time, that's where everything attracts onto. That's how smoke visualization works. All of the smoke attracts on to those vortex structures. Okay, and that's why you get these cool filaments. So the way you actually compute this is you create a grid of particles, you integrate them all forward or backward in time, you zoom in, this is just a zoom in to 4 neighboring particles in a stencil here. So these 4 neighboring particles might have flowed here. Sorry, you can't read this at all. But these 4 particles stretched in some directions and compressed in others. And that you can approximate this, the Jacobian of this flow map using finite difference derivatives of these few final positions with respect to these initial positions. This is a matrix of partial derivatives. And then you look at the maximum singular vector, a singular value. You take the singular value decomposition of this matrix, and the largest singular value tells you how much those particles stretched in time. And the regions that have the largest singular value are the ones that I color red here. Okay, that's how you compute these finite time Lyapunov exponents. And so these are super duper useful in fluids to tell you lots of interesting things about what the flow is doing. This is a video by Shadden, DeBerry, and Marsden. This is one of my absolute favorites. They measured the flow field behind a jellyfish, and then they integrated like imaginary particles forward and backward in time to find these Lagrangian coherent structures. And what this does is it explains that the blue fluid that starts on the outside stays on the outside. It gets shed into this propulsive wake. That's how it moves forward. And all of this green material that started on the inside gets entrained into the bell. This is how they eat. And so this is the first visualization that, from a dynamical systems perspective, explained how jellyfish simultaneously propel themselves and feed with the same periodic motion. Okay. This one's really cool. This is also John DeBerry and Kit Parker, Caltech and Harvard. So they decided to take this idea and build a robo-jellyfish. So they implanted cardiac cells from a rat onto this little mold, and they put this in a dielectric fluid and pulsed it, and they created a robotic jellyfish. They call it a medusoid jellyfish. And now they're going to turn the pacing on, and they've created this little jellyfish. Very cool. Yeah, I really, really like this video. But they understand a lot more about the physics of the system by analyzing these Lagrangian coherent structures, these regions where the Lyapunov exponent is positive for some amount of time. So unfortunately, a lot of our understanding of these dynamical systems is to understand how to dump pollution. I'm not kidding. A lot of our understanding about dynamical systems and fluids comes from either we accidentally dumped a bunch of pollution, or we want to dump a bunch of pollution, but we don't want it to stay near where we live. And so, this is a video of the Gulf oil spill. So you can compute those regions of separation or attraction, and you can figure out where is the oil going to attract to, where is it going to repel from. And actually, you get very good predictions of where the oil plume will be. This is Monterey Bay in California, one of the most beautiful bays in the world. And they asked a very simple logical question. If we're going to dump our pollution into Monterey Bay, where should we dump it so that it goes out and doesn't recirculate? I mean, this is crazy. But this is where this came from. And you can see this large recirculation region here separated by this manifold. So if you were dumb enough to dump pollution in Monterey Bay, you would dump it to the left of this jut, because then it'll go to the ocean. And if you dumped it to the right, it's just going to recirculate in the bay for a really, really long time. And anytime you go to a river, you see this. You see the scum on the side that just recirculates there forever. Okay? Those are quantities that you can pull out from dynamical systems analysis. Those are from the manifolds. And I'll point out that these also tell you where you would control your flow, where you would want to put an actuator if you wanted to get the most change in your flow. Those are given by these positive Lyapunov exponent regions. Okay, so that brings us back to this original figure that I showed you at the very beginning. You can use these for full coupled climate simulations, and people are doing that right now. You can use this to figure out where the ocean is mixing a lot, where it's not, where someone is going to get pulled out to sea. They use this for rescue missions now. On coastal regions and all kinds of interesting things. Okay, that's everything I have for dynamical systems right now, but I'm happy to answer any questions if you would like.
Questions?
Okay, Bernd has a question.
I have a very simple question. So how, in principle, there are myriad or a hierarchy of reduced order models which can describe something. And I think a challenge is figuring out something like a good cost function, which really assesses what we want to have from these reduced order models. To some extent, determining the cost function or the quality function of a reduced order model is more difficult than the actual construction. Any thoughts on that?
So this is a fantastic point. Maybe I'll just re-say this. So when I'm building a model of the world or of my system, it's not one model. There's infinitely many models I could build to describe more fidelity but more expensive, less fidelity but less expensive, and every reduction in between. How do you pick the best one or the right one? And I think this is actually an excellent point, and that's going to segue very nicely into the second lecture I'll give in the afternoon, is this idea that in model reduction or system identification, you have to be extremely clear about what you want your reduced model to do. What is a figure of merit or an objective that says it was a good model or a bad model? And I completely agree with Bernd that writing down the right objective function, the right optimization problem, is almost always the hard part. Solving the optimization problem is oftentimes like a standard algorithm you can download off of GitHub now. Okay, does everyone want coffee? One more question and then coffee.
About the example with the metronome, has anybody actually controlled that? Because usually we know, it's a common thing, we know how the system is going to end up. Has anybody tried to make it faster, or would it be a crazy amount of energy to just make it go faster to the end state, or to keep them out of phase?
That's a really, really good question. There is a vast literature of network control and the control of networked dynamical systems. And I can't even begin to kind of outline that field. It's very large, and I only know a very little bit about it. People definitely think about control. A lot of times they think about malicious control or sabotage. So, for example, our internet system is a big network of coupled routers, okay? And could you design a control law to cause that network dynamical system to fail as fast as possible? Same thing with the power grid. So people think a lot about how robust your system is to targeted attacks versus random attacks. That doesn't necessarily answer your question about the metronome specifically, but it's a huge field of study to understand the robustness and manipulation of networked dynamical systems in general, and that's just a very simple toy network dynamical system that we use to test methods when we care about things like the power grid and the internet. Yep.
So other questions? Otherwise we go for the break. It seems we go for the break. Then thanks again to Professor Pronto for this.
Thanks.
Nice review.
Huh? Is it on? Oh, yeah, no, it's on. It's on. Yeah. Okay, welcome back, everybody. How's everyone doing? Good coffee? Yeah? Okay, so this next lecture is going to be about system identification. And this is such a short amount of time to tell you anything meaningful at all about system identification. System ID is an extremely rich field. It's been in full force for at least the last 50, 60, 70 years. And so I'm going to tell you about the most kind of briefest part of system identification. So I'm just going to give you a kind of blanket definition statement. System identification is learning a dynamical system model from measurement data. Okay? That's it. You don't start with a model. You have to build your model from your data. That's what system identification is. So you collect measurements, you build a model of those measurements, and again, we're always interested in the balance between accuracy and efficiency. Okay? There is a dual side of this. You can't really talk about system identification in a fluids context without also talking about model reduction. And I see these as being very related, almost dual concepts. Model reduction is where you do have a model, Navier-Stokes or something similar, but you want to simplify it because the original model is too big or too complex for whatever objective you have. Okay? And these are related. You use a lot of the same tools and techniques, mathematical architectures, for system identification and for model reduction, but they start from different places. System identification is purely data-driven. Model reduction, you start with some governing equations. Okay? And I have thought a lot about what to talk about today in this hour because it's such a brief time. I actually prepared a bunch of whiteboard, but I figure that I only get one shot on this whiteboard. And so I'm going to punt a little bit, and what I'm going to point out is that there are two chapters on classical system identification, linear system identification, in the book I just wrote with Nathan Kutz. And so I'm going to just completely punt. You can download the entire book at databookuw.com/databook.pdf. So this is not just a shameless plug. Like, you can download this PDF, and all of the system identification is in this book in chapters 9 and 10. And all of the lectures for all of that classical linear system identification are on YouTube. And it's 5 hours, 6 hours, 7 hours. So I'm not going to try to compress that into this 1 hour. Okay? It's very technical, and it requires a whiteboard. So what I'm instead going to do is I'm going to give you the very high level of what kind of classical system identification does. And I think what will be more interesting for all of you, and will segue much more naturally into tomorrow's lectures on machine learning, is I'm going to talk about what are the modern cutting edge tools in system identification that we're using today. Okay? Good. All right, so again, I would probably say that 90% of the techniques in system identification are for linear system identification. Why is that? Because it's all that we can work with and have any kind of guarantees or generic tools. Linear systems are the only systems where I have one-line solutions in MATLAB for control and estimation. I mean, all of you have heard of the Kalman filter. And a lot of the modern era of work on system identification started with Kalman and Kalman filtering, okay? So I'm just gonna have like 2 or 3 slides on linear system identification, and then I'm gonna move to more modern stuff. So here's a system. So the basic idea of model reduction or system identification is, this is a model reduction problem. Here's a model, it has 2 states. Do I need to pay attention to both states? Are both states equally important? If I only had enough computational power to pay attention to one state and to simulate a one-state ODE, which one would I pick? This is like a real simplified version of what you're going to face every day in fluid mechanics. You have a billion states. What states do you pay attention to? If you only can afford to pay attention to 5. Okay, so just any thoughts? Which state matters more, x1 or x2? How many of you think x1 matters more? How many of you think x2 matters more? Okay, why do you think x2 matters more? I would completely agree with the x2s because it has a slower time constant. x2 is going to be around a lot longer. It's our future. Okay, x1 is going to die out long before x2 does, so we're going to have to pay attention to x2 for longer. So if I only get to keep one state, I'm going to keep x2. Except this is not the whole story. Okay, I gave this example to trick you. What if I have a control input and a measurement output? Now which state matters more? Clearly x1, even though it's more damped, and if I only looked at the A matrix, x1 would be the less important mode. Now that I have control inputs and measurement outputs, clearly x1 is far more important than x2 because x2 is barely affected by my control input and it is barely observable by my sensors. It practically doesn't exist to my control system. Okay, so you have to really think about a lot of different things when you're doing model reduction. There's a whole field of model reduction called balanced model reduction. This started in the 1980s with Moore, and then it entered fluid mechanics with Wilcox and then Rowley in the 2005 time period. And there's a bunch of great papers on balanced proper orthogonal decomposition. Basically, how would you find modes? So remember, you have your big fluid, and a way of finding a few numbers that matter would be the POD. So Barrett has showed you, or who did POD? Okay, so you saw the POD, Scott did POD. So you know that that's one way of doing model reduction. You have a million-dimensional system, you do the SVD or the POD, and you get 5 or 6 or 7 states out that matter. But again, that only was half of the story. That if you had control inputs and measurement outputs, those might not be the best modes. And so instead, there's this idea of balanced model reduction, where there are these things called observability and controllability Gramians, which tell you in your high-dimensional state space which states are most controllable and which states are most observable. So if we go back to this system, the x1 state is far more controllable than the x2 state, and the x1 state is far more observable than the x2 state. And so that would basically say that certain directions are much more observable and controllable than others. And so what the balanced POD tries to do is find a coordinate transformation into a new coordinate system. Remember, just like the eigenvector coordinates, you're trying to find a coordinate transformation into a new system. And these are eigenvectors of another matrix, where these Gramians are equal and diagonal. And then you basically keep the directions in state space corresponding to largely observable and controllable directions, and you throw away the weakly controllable and weakly observable directions, like in that simple 2x2 example. So that is a huge field of work that people do every day. That's all I'm going to say about that. Okay, except this is just one little example of how to do this. Okay, so let's say I have this system here, x1 equals -1, -10, so the x1 dynamics stay around longer than the x2 dynamics. And you'll notice that my actuation matrix and sensor matrix are kind of opposite of each other. So the x2 direction is much more controllable, and the x1 direction is much more observable. So I want to find a coordinate transformation that balances these two. And I like this example because to some extent, I chose this to be an issue of units. I basically said, okay, let's say I am measuring Z1 in like millimeters, and I'm measuring X2 in kilometers, so that all of these numbers are just messed up. So all I'm going to do is I'm going to introduce this coordinate transformation that scales X1 up by 10 to the 3 and X2 down by 10 to the -3. I'm not going to get to eat this. And if you introduce that, this is the balancing transformation I talked about. Now what you have is a balanced system where the control and the sensing are equal to each other. So now if I wanted to truncate the system, which one would I truncate? The ball's in your court. Which state in z coordinates would I truncate? I would truncate the z2. Because all things being equal, now they are equal, these are equal and they're equal to each other, and it's all decoupled, the Z2 dynamics are gonna die out much, much more rapidly. So I'm gonna see their effect less. So if I only kept the Z1 equations, I would keep most of the input-output dynamics. So that's what this balancing does for you. It allows you to then make your decision based on the matrix A again, okay? Good. Okay. So, this was the picture I showed you before, system identification, model identification. That's all I'm going to tell you about model reduction. Now I'm only going to tell you about system identification. Good. And again, back to our lecture on dynamical systems, there are kind of three big challenges that I think about a lot in system identification. One is, our equations are unknown, so that is the whole foundation of system identification, is discovering these. The second piece is that our nonlinear dynamics are poorly understood. So if in the process of discovering my model, I can also discover some coordinate system where that model becomes simplified, I want to do that. Okay. And high dimensionality is a big problem. Okay, so we're always going to be doing something like POD as the first step of this. Okay, and so I'm going to mostly focus on the first bullet of discovery here. Okay, and I'm going to walk through a few different things. So you have heard about dynamic mode decomposition, yes? All right. Peter Schmidt told you about dynamic mode decomposition. I'm going to give like 2 slides because it is a system identification technique, and I want you to see it as a system identification technique. Then we're going to talk about Koopman operator theory, which is kind of one of the main use cases of DMD. Then we're going to talk about nonlinear system identification. How many of you have heard of Koopman operator theory? Okay, everyone. I'm assuming Peter probably mentioned it. Good. All right, so I'm going to talk about it a little bit. So this is just a bunch of examples of dynamic mode decomposition. It's a little nerve-wracking to give this lecture with Peter here because he invented the dynamic mode decomposition, and I'm just, we're basically just users. So remember, we think about dynamical systems as movies. Okay, that's what they are. They're movies. They vary in time. There are frames in a movie. And so I can take my flow past the cylinder. I can take every frame in this movie and arrange them like this. I can then build these matrices X and X prime, where each column of X is a frame of my movie that's been reshaped into a very tall, skinny vector, a million-dimensional vector. Okay, and each column is the state of my system evolving in time. Okay, so this is the kind of data you might have access to when you're doing system identification. DMD is one approach to build a model from the kind of data you would be using for system identification. I have a time series of snapshots of my dynamical system, and I'm trying to build a model to describe the evolution. Okay? And as you know, the DMD is essentially this least squares regression, this best fit linear model that advances X into X prime. Each column of X, it would advance those columns forward one time step forward in time. So you've seen this before. Now, DMD has some super cool features because this A matrix, if X was a million tall vector, then this A matrix is million by million. And so you don't want to compute it. You don't want to put it in memory. You especially don't want to compute its eigenvalues and eigenvectors, right? And so the DMD is a set of extra linear algebra techniques to find the leading eigendecomposition, the leading eigenvalues and eigenvectors of A without ever actually computing it. And so, for example, you compute an SVD of X and you work in this reduced subspace, right? Good. And that's what we do in a lot of system identification techniques when you have high dimensional data, is you first find some low dimensional space where you can project onto, okay? I stole this slide from my wife. This is how she thinks of the DMD and explains it. It's like if principal components in space and Fourier transform in time had a baby, it would be adorable. And these are two of the most important algorithms of the last century. Okay, so it's no wonder that DMD is extremely useful and is being used in lots and lots of fields beyond fluid mechanics as well. Okay. Good, but I think of this as a system identification technique where you get a linear system x prime equals ax. Okay. This is the original paper, and there's some fantastic examples in here. I really think you should read this, and I'm not just saying this because Peter's in the audience. I really, really love this paper. There are individual sentences buried on like page 12 and page 17 that you could find an entire paper to write, and so that's pretty cool. After the original DMD paper, of course, there was a strong connection to Koopman operator theory, to nonlinear dynamical systems. So you should be wondering in the back of your head, why are you saying that you can model a nonlinear dynamical system like Navier-Stokes? We know that that limit cycle is a Hopf bifurcation, so there's some nonlinearity happening in this flow. Why can I model that using these linear evolution operators? And so it's this deep connection to Koopman operator theory that I'm going to tell you about later. That I think makes this a nice story, and this was developed by Rowley and Mezich and collaborators. There's a cool video. I stole this from my wife. She makes way cooler DMD videos than I do. So she gets this question all the time about what's the difference between DMD and independent component. How many of you have heard of ICA, independent components analysis? Okay, it's like a statistics tool for separating sources that have different dynamics like this. And so this is what PCA would give you. It mixes those two signals, right? Because PCA is only based on the energy or the variance in the signal. And when I say PCA, you should also be thinking it's the same as POD. Okay. ICA actually does separate out the square and the Gaussian that are oscillating at different frequencies, but it has a bunch of noise and clutter. DMD perfectly separates them, and it gives you the eigenvalue of how those dynamics evolve. It gives you a model, not just the modes. Okay, and since its origination, it's been applied to tons of different systems, weather and climate, neuroscience, lots of other fluid systems, disease modeling now, robotics, and things like that. So, and one of the things I will tell you later on in this lecture, one of the things I like about DMD is it is a very simple formulation of an important problem in terms of linear algebra. And if I can give you one piece of advice, and I'll probably give you this again, you should become linear algebra ninjas. That is like the most useful thing you can pick up, is good skills in linear algebra. If you can pick up 2 things, get really good at optimization. And if you have time for 3 things, learn statistics too. Okay? But linear algebra is everything, especially in model reduction and system identification. And the DMD formulation has been extremely extensible. It's easy to extend it to include control and partial outputs and nonlinearity and all of these other aspects. So I think of it as kind of this unifying framework. And it actually ties into decades of system identification research that I'll tell you about. Okay, so how many of you have heard of the eigensystem realization algorithm or the singular spectrum analysis? Okay, from climate science. There are deep connections between DMD and those classic techniques. Okay, good. So this is a little dangerous because I actually don't know how much you know about Koopman operator theory. So I'm just going to give you what I think is important from Koopman operator theory, okay? And for me, it's all about the discovery of coordinates. So system identification is about building models from your data, okay? And I see model building as having 2 equally important legs, okay? One of them is building the model itself, like what is f of x? The other part that's equally important is what are the right coordinates to build your model in terms of? You might measure x. How do you know that's the right variable to build a model on? Right? Like in fluids, we have some theoretical justification that vorticity might be a good variable, okay? But in lots of systems, it is not obvious what variable you should be using to build your model. Even in planetary dynamics and astrophysics, it took thousands of years for humans to discover the right coordinate system to describe the model for the motion of the planets. Okay, that was a coordinate system. And so that's what I'm going to talk about with respect to Koopman operator theory is this is a way of finding a coordinate system where your nonlinear dynamics become simple and linear. Does that everyone follow? And again, please interrupt me if you have any questions. This is confusing as hell the first time I thought about it. So we're going to now be talking about this part of the system identification problem. Nonlinear dynamics are very poorly understood, and we want to build coordinate transformations where our systems become simpler. And in this case, when I say simple, I mean linear. And it's kind of this miraculous statement that shouldn't, be obvious that it's true, that for large classes of nonlinear dynamical systems, pretty much almost all of the nonlinear dynamical systems we're interested in, there are coordinate systems and coordinate transformations, ways of viewing the system where even very nonlinear dynamics look linear. They look like exponential growth or decay in sines and cosines in those coordinates. And this is a theorem from Bernard Koopman, 1931. He wrote this down. So he was trying to help build the mathematical foundations of quantum mechanics, Hilbert space, and relate Hilbert space and dynamical systems. And in doing so, he realized that if you have a nonlinear dynamical system, there is a Hilbert space, this infinite dimensional function space of all possible ways you could measure that system. So I've got a system dynamics, x dot equals f of x, super nonlinear, but I can measure that system in an infinite number of ways. I can measure x1 squared times x2, or x3 sine x1 cosine x2. There's an infinitude of ways of measuring that system. It forms a Hilbert space. And what Bernard Koopman showed is that the nonlinear evolution in state space becomes a linear evolution in this infinite dimensional Hilbert space. So your nonlinear dynamics are linear in an infinite dimensional measurement space. That's this paper here, Hamiltonian Systems and Transformations in Hilbert Space. A little bit of history. It turns out that the Koopman operator theory was the missing piece that was used to solve the ergodic theorem by von Neumann and by Birkhoff independently. So for those of you who remember, Maxwell and Boltzmann described the statistical description of gases. And the Koopman operator theory was the missing piece to tie up the mathematical theory, and that's what von Neumann and Birkhoff did in the same year that Koopman wrote this paper. Okay, so super important at the time. There's a nice history in PNAS about this. And so at the time, no one realized that this was important for nonlinear dynamical systems. This was useful for the statistical theory of gases. Okay, and it's only recently that Koopman theory has had this resurgence. And a lot of it is due to Igor Mezich and various colleagues and collaborators. And actually, I would argue a lot of it has to do with the DMD because that's the engine we use to find these coordinate transformations. Okay, so when I say that there is an infinite dimensional linear operator that involves all possible measurements I could take of my system, you should be thinking, when I say infinite measurements, you should be thinking big data. Okay, we're collecting lots and lots and lots of measurements of complex systems now. We have more measurement capability than we've ever had. And the idea is that the more measurements you have, the more linear your system becomes. And it's a very powerful perspective. So this is almost philosophical at this point. I want to show you on a very concrete example. Okay, and how many of you have seen this example before? Okay, good. So I'm going to walk you through this. This is a very simple nonlinear dynamical system with two variables, x1 and x2. In fact, the x1 equation is linear. x1 dot equals mu x1, just linear dynamics in x. x2 is only a little nonlinear. It's lambda x2 minus x1 squared. And I'm going to assume that lambda is a fast eigenvalue and mu is a slow eigenvalue, just because it makes my conceptual life easier. So what that means when lambda is fast means that x2 very rapidly equals x1 squared. And so initial conditions will quickly attract onto this red manifold and then slowly go to the origin if they're both stable eigenvalues. Okay, so this red thing is called a slow manifold, and the dynamics rapidly equilibrate onto this. So that's what the dynamics do. And what I want to convince you is that there is a coordinate system that if I wrote these dynamics in this new, better coordinate system, everything would become linear. Okay, and here's the coordinate system. So I'm going to build this three-dimensional system so that y1 is x1, y2 is x2, and y3 is this nonlinear function x1 squared. And we're going to go through these operations and make sure that the dynamics in y coordinates are in fact linear. Okay? And why do I want linear dynamics? Because we're lazy. We want to use one-line MATLAB commands for optimal control and optimal state estimation and future state prediction. I don't want to simulate this thing and do nonlinear optimization, right? I like one-line commands. So I want linear systems. Okay, so y1 dot is x1 dot is mu x1, which is mu y1. So that's still linear. The y2 dynamics are interesting. y2 dot is x2 dot. And x2 dot is lambda y2 minus lambda y3. Okay, so that linearized my second equation. And all of the kind of magic happens in this third equation. So what is the derivative of x1 squared? Well, it's 2x1 x1 dot. And 2x1 x1 dot is 2 mu x1 squared. And 2 mu x1 squared is just 2 mu y3. So y3 dot is closed in this coordinate system. Its derivative is also in this coordinate system. And so I really get this linear 3x3 system that describes these nonlinear dynamics. Okay, there's no magic here. It's pretty simple. And here, are the trajectories, the same white trajectories in that three-dimensional space. These are linear evolution dynamics. And when I project them onto the y1, y2 plane, you can see that they have this same behavior here. Okay, so nothing magic is happening. And it turns out that for all nonlinear dynamical systems, there are some coordinates where they will look linear. And our job is to find those coordinates. And that is really hard. Okay, if it was easy, I picked the one example where I can do it easily. Okay, it's really hard to find, in general, these coordinate transformations where this works. But does everyone appreciate why we want to do this? It makes our lives so much easier to make things linear. Okay, and I'll point out that if you look at the left eigenvectors of this matrix, you get essentially these nonlinear observables, x1 and x2 minus bx1 squared. And if you measured your system in these phi coordinates, phi lambda has dynamics that look like e to the lambda t, and phi mu have dynamics that look like e to the mu t. They really are linear if I view the world in those coordinates. Okay. Okay, good. So why doesn't this work? We're going to talk about this equation. Now, this one looks even simpler. X dot equals x squared. Can anyone tell me what this system is defined? What characterizes this dynamics? Give you a hint. You can't talk about it in an airport because it blows up in finite time. Okay, so I can only talk about this after I land. So we're going to try the exact same trick. We're going to try to build an augmented state vector with some nonlinear terms so that our dynamics close. And so since I have a right-hand side x squared, I'm going to try to put an x squared in my dynamics. Okay? And it's nice because y1 dot does in fact equal y2, so that's good. But now when I compute my ddt of y2, I get 2xx dot, and now I get 2x cubed. Shit. So now this is not in my space. So the derivative of y2 is not some linear combination of y1 and y2. So I need to add a y3, which is x cubed. And when I take its derivative, I get an x to the fourth. So I need to add an x to the fourth. When I take its derivative, I get x to the fifth, and so on and so forth. It doesn't close, ever. So Koopman says that you get linear dynamics, but you really do need an infinite dimensional basis in general. It's only linear in an infinite dimensional representation. Okay, so this is the rub, is that we want to find these magic coordinates, but we can't often, or at least we can't represent them in easy coordinates. Polynomials are like as bad as you could possibly use for coordinates. I mean, most of you know that, but it's an illustrative example. What is interesting is that if I truncate this system at order 2, order 3, order 4, we do get closer and closer to this observed finite time blowup behavior, but it really doesn't do the job. Okay? So I showed this to Clancy Rowley. We were waiting for a bus to go to a workshop in Florida. And he literally just scratched on a napkin the solution. This is the magic function that if you measure in that coordinate system, everything is linear. And it's simple, e to the minus 1 over x, obviously. If you measure the system in these coordinates, d dt of that function is just lambda times that function. Okay? So this is what my wife calls the Feynman method of solution. You scratch your head and you write down the answer. Okay? But this doesn't work for more complex systems. You're not going to write down the magic eigenfunctions for turbulence. Okay? And I'm actually quite convinced that he had thought about this exact problem before, now that I've thought about it. So this is now a homework problem in my intro math class. What you do, sorry, this is the wrong slide. My apologies. I'll show you how to derive this. It's a homework problem in my intro math class. I'll show you in just a minute, okay? But I want to take a step back. So the Koopman operator theory, we've already seen kind of the Poincare geometric view of dynamics. This is how we computed the finite time Lyapunov exponent. We followed trajectories. That's what we've been doing for 100 years, is follow trajectories and find manifolds. But there's this new kind of operator theory that's working instead of on trajectories of x, it's operating on measurement functions of the state g. G is a function. It's not a trajectory, it's an abstract function in a Hilbert space. It has an infinite dimensional representation. And in that representation, the Koopman operator linearly advances those measurement functions forward in time. So if I have a measurement g of my system at time k, if I hit it with this linear Koopman operator, it advances me to the next time step. Okay? And what I showed you in those simple numerical, those simple 2x2 and 3x3 examples, is that what I want to do is find something called a Koopman invariant subspace. I don't want to work in an infinite dimensional function space. I want to have 3 observables where if I measured my system in those 3 observables, I get a closed 3x3 linear system for how they evolve. Those are defined by these invariant subspaces, so that if G is a combination of M observables and I hit it with Koopman, it's still in the span of those M observables. That would give me an M by M matrix that would evolve my system linearly forward in time. Okay? And so that's what we're trying to do in this is nonlinear system identification. We're trying to find those invariant subspaces. We're trying to find these functions that when I observe my system in those functions, they behave linearly in time. Okay, so here's where I'm going to show you how you find the solution of x dot equals x squared. So we had our original dynamics x dot equals f of x. We're trying to find these special magical coordinates phi of x so that they behave linearly in time. Yeah? And these phis are eigenfunctions of the Koopman operator, and the lambda are eigenvalues. So that's what the coordinate transformation means. These are just an eigendecomposition of the Koopman operator. And so what I can do is I can apply the chain rule to this quantity here. So I can get the grad of phi of x dotted with x dot, which is grad phi dotted with f of x. That's what the time derivative of phi of x equals. And that has to equal lambda phi of x. Okay? This is a partial differential equation for Koopman eigenfunctions. It's a really ugly PDE. I've shown this to my friends who specialize, whose careers are solving PDEs, and they tell me it's very nasty and hard to solve. Okay? But at least in 1-dimension and 2-dimensional dynamical systems, you can actually analytically solve for the Koopman eigenfunctions. Okay? Pretty sure that's what Clancy did. I'm assuming. I'll ask him next time I see him. If you take this differential equation, what you can do is you can assume that phi of x has an expansion, a power series. Actually, you need to assume it has a two-sided power series, a Laurent series. So it is a sum of positive integer powers of x and negative integer powers of x. And you take that Laurent series and you plug it into this PDE and you solve for all the coefficients like you do. This is how Bessel's functions were derived. And what you get out is the power series expansion, the Laurent series for e to the minus 1 over x. You can solve for the series representation of the solution of this eigenfunction for simple PDEs. Okay? Any questions? That's a lot to digest. Yes?
So if you look at the Liouville equation,
Yes?
this seems to be the eigenequation of the Liouville equation from this would be... So the Liouville equation would be partial t plus f
Dotted with grad.
nabla p.
Yeah.
And so this is the eigenequation of the Liouville equation.
Yeah, so this is absolutely right. This is the eigenequation of the Liouville equation, which is the continuous time analog of the Perron-Frobenius equation, which is the dual of the Koopman operator. These are essentially all cousins. It's a big family of operators. And the idea is that you can take your nonlinear dynamical system, and if you think about how probability densities of trajectories evolve through that system, or how measurement functions of that system evolve, those can be seen as linear dynamical systems, but in an infinite dimensional space. Again, I can't tell you about all of this in an hour, but the keywords are Koopman, Perron-Frobenius, and Liouville. Okay, if you Google those, you'll find this rich connection between all of those different theories. And so in practice, what we do is we try to approximate these functions phi as some expansion in a basis. You pick a basis, you measure a lot of data, you do a regression that's basically a DMD regression, but onto nonlinear functions of the state, and you try to approximate these eigenfunctions doing that. And that's what this extended dynamic mode decomposition does from Williams, Kevrakidis, and Rowley. So they were the first, at least in the Koopman context, to show kind of how you would get these nonlinear eigenfunctions from data in a dynamic mode decomposition framework. Now it turns out, and they applied it to some cool systems like this Duffing one that we worked on earlier. Okay, it turns out that in the chemical kinetics community, they actually discovered this about 3 years earlier, which I find really interesting. So I think it was Kloos and Noe and others developed this for molecular dynamics also in parallel. And so there's kind of two groups of people developing this, and we should try to learn from the molecular dynamics people because they're about 3 years ahead. Okay, so this is your PDE for eigenfunctions.
But we have a question.
Oh, another question, yeah.
It's not a naive question, but it is perturbing me a little. In order to have these modes, you can ask yourself first, do they exist? I mean,
They have to
do
exist.
Koopman operator do have eigenvalues? And it turns out that if you take for topology, for Hilbert space, the Hilbert space L2, for instance, then the spectrum of the Koopman operator is continuous, and there is no eigenvalue. So how to get these eigenvalues, knowing that the Koopman operator has purely continuous spectrum? Or, another way to put it, can you change the Hilbert space in order to get eigenvalues? Sorry.
Yeah, so it's a really good question. This is not an intro question, and I would like to translate this question a little bit for those of you who might not have followed that entirely. Okay, so I said that there is this Koopman operator, and it works in this Hilbert space. You should be thinking, well, what's your inner product? What is your Hilbert space? Which space of functions are we talking about? And it makes a huge difference to whether or not these things are or are not amenable to solving for these eigenfunctions and representing them is the choice of Hilbert space. That's a very technical consideration. Lots of people are working on that. It's not something that I work on, but I know that lots of people are thinking about alternative Hilbert spaces. So Dimitri Giannakis and Andrew Stewart and Krithika Manohar are all working on this. The second part of your question, there's something called a continuous spectrum. How many of you have heard of a continuous spectrum before? It's a really interesting and messy concept. It's actually closely related to chaos and mixing from the last lecture. And I'll tell you a little history. This will be a little bit of a diversion. So I was sitting in a workshop on Koopman operator theory at United Technologies 5 years ago. Everyone was excited about this. There was about to be, millions of dollars of grant funding to study Koopman theory. And, we're in this room, everyone's talking about their latest and greatest technology. And I asked the question, how do you use this to solve the pendulum? Because if I can't do Koopman operator theory on my simplest textbook example of a pendulum, no one's going to use it, okay? And it turns out I didn't know about continuous spectrum 5 years ago, and this is the simplest system you can think of that has a continuous eigenvalue spectrum. So what it means is literally, if I have my pendulum and it's in the down position and it's linearized, it has a pair of eigenvalues, plus and minus I omega. It has one distinct frequency, natural frequency. But as you slowly increase energy of the system, that frequency gets lower and lower. The period gets longer and longer, until eventually, when it's in the up position, it has an infinite period, so to speak, right? It would take forever to get back up to the top, which means it has zero frequency. So if you look at the complex plane, and my original eigenvalues were plus or minus I omega, if I look at the nonlinear pendulum, it has every eigenvalue between them. That's a continuous spectrum of eigenvalues. And that's one of the Achilles heels of Koopman operator theory. It is very, very hard to find a discrete representation for any system that has a continuous spectrum. We're still trying to figure this out. And if I can get to time delays, it turns out the time delays are how you handle this in practice. Yes?
If I speculate, so this is the eigenequation of the Liouville equation. The Liouville.
When Bernd speculates, great things happen.
So the Liouville equation essentially is on L2, so the phi are normalized so that the integrals over the phi in the whole space is unity. And if something is L2, it should have a discrete spectrum. So a countable infinity, but discrete spectrum. So this would be my best guess for this spectrum.
This certainly sounds reasonable. I'll admit I am a practitioner. I like collecting data and doing regressions, okay? There are lots of technical issues here of finding the right inner product, finding the right coordinate system to find discrete spectrum. You want a discrete spectrum because when your eigenvalues are discrete, they have their own eigenfunctions that are these special measurement functions that you can work with, okay? So a lot of what you do here to approximate these things is you assume that your phi of x can be expanded in some basis theta. So you have some basis of functions theta, and you're going to say that your eigenfunction is some linear combination of those basis functions. Maybe these are Bessel functions, maybe they're trigonometric polynomials, whatever basis you like, okay? And we're just going to expand it out. And essentially what you can do is you can build a data matrix of theta evaluated on trajectories. And you can build this gamma matrix that's basically all of this stuff on the left-hand side. It's just grad theta dotted with my dynamics. This is also a data matrix you can literally build from data, just like in DMD. This is basically x and x prime, okay? And now what you're going to try to do is this linear regression to find the eigenvectors of theta dagger, theta prime in discrete time, or gamma dagger theta, or sorry, theta dagger gamma in continuous time. And this is exactly what the extended DMD algorithm and this VAC algorithm, and it was Noe and Niske, sorry. They were the ones who discovered this in 2013 for chemical kinetics, okay? So it's basically a DMD regression, but you're expanding your eigenfunction in some nonlinear basis. So you're augmenting with nonlinear measurements and doing that regression. Okay, that's what the extended DMD is doing. Okay, great. Any other questions about this? Yeah, in the back.
So you mentioned that we can take a basis and then find the coefficients for that basis and get the function phi. So I was thinking if we had taken that basis to get the Koopman operator in that basis, would we get like a low rank Koopman operator?
Yeah, so basically if I just pick a few of these lambdas and x's, I get that's model reduction. I can pick some subset of my eigenvalues and eigenfunctions, and that is a lower dimensional representation that is itself linear and captures some features of my original system. Yeah. So actually a great example of that, this reminds me, a good example of a continuous spectrum system like the pendulum or the Duffing example or lots of other systems, those systems have a Hamiltonian, right? The pendulum has a total energy that's conserved if there's no friction. Any conserved quantity is a Koopman eigenfunction with eigenvalue 0, because ddt of energy equals 0 times energy. Okay, and so that's actually a very useful Koopman coordinate system where all of the conserved quantities of your system are eigenfunctions with 0 lambda. They're in the null space of this operator. So that's very, very useful. And Ulrike Kaiser has written a beautiful paper showing that you can use that for control. Okay, good. Okay, I'm going to talk more about dynamical systems. I got 5 more minutes, and we're going to talk more about dynamical systems. And I'm just going to keep talking until I can't talk anymore. So this lecture is about system identification, but if you want, grant money, you call it model discovery. So it sounds so much more exciting to discover a model than to identify a system. So again, I would just highlight that system identification has been around for decades and decades and decades, 70 years of active research, tens of thousands of good papers. This is a tiny, tiny, tiny fraction of some of the modern papers that use machine learning for system identification. And what I'm highlighting in pink here is this recent trend to discover models that are so-called parsimonious. And parsimonious is just a fancy word for greedy. And what do I mean by greedy? Remember, we're always balancing accuracy and efficiency. Okay, and what I want are the models that are as simple as possible, but no simpler, or as complex as they need to be, but no more complex. Does that make sense? That's what we want. That's a parsimonious model. And oftentimes we're going to achieve parsimony by sparsity. That means we want as few terms in the model as possible, usually. Okay? So I'm going to tell you this is now kind of active work in my lab, but lots of other people are working on this too now. So I'm going to tell you about the sparse identification of nonlinear dynamics. We call it SINDY. How many of you have heard of this? How many have not? Oh, that's my favorite thing to see. Good. So I'll tell you about SINDY on the Lorentz example, and then I'll probably tell you a little bit more about this tomorrow applied to fluid systems. Okay. So remember, this is the Lorentz equation that has chaos, and it's a model for Rayleigh-Benard convection. And so it's a 3-state ODE. And if you look at it, it is nonlinear, but it's actually it's surprisingly simple. For how complex the dynamics are, the equations are relatively simple. There are only a few terms in each equation, and there's only a couple of truly nonlinear terms. There's an xy and an xz, okay? And so the idea here is we want to, let's say that you didn't know what these equations were, and you wanted to discover, so now we're back to model discovery, discovering f of x, okay? We want to discover this right-hand side, but all we have are measurements of x, y, and z in time, and measurements of the derivative in time. Okay, that's the system identification problem. I measure time series of my data, and maybe I can compute derivatives, and that's all I have. So what would the dynamic mode decomposition give us in this example? So it would give me a 3 by 3 matrix right here, and it would be the absolute best fit linear operator that could possibly map x, y, and z into x dot, y dot, and z dot? How many of you think that you're going to capture the Lorentz dynamics with the 3x3 linear matrix? You can't, right? This has multiple fixed points and unstable periodic orbits. It's fundamentally nonlinear. And if we measure x, y, and z, there is no linear model in x, y, and z that can capture these dynamics. So kind of building on this idea, though, of doing a linear regression on data, what we're going to do is we're going to augment the right-hand side of this library to include nonlinear functions of our state, similar to what we did when we were trying to find Koopman operator eigenfunctions. We're going to assume that there's some space of functions theta, and we're going to assume that my right-hand dynamics can be written as a linear combination of columns of theta. So instead of just x, y, and z, I can build x squared, xy, y squared, all the way up to z to the 5th. And these columns can be evaluated from data. These can be built just from the data I have here. I can take x and y and z, and I can compute x squared and xy and y squared and things like that, okay? And so here's the key observation. We expect that almost every nonlinear dynamical system we've ever seen has been sparse. Open a textbook and find me a dynamical system that's not sparse. I challenge you, that's homework, okay? This is somehow sparse in the space of all the right-hand side functions that this could have been. This one's quite simple, and there's only a few terms. That's what I mean by sparse. So now what we're trying to find, this is the coefficient matrix that if you multiplied theta, you would get x dot. This is like the truth that I know. We're going to try to find the fewest columns of theta that add up to explain x dot, and the fewest columns that add up to explain y dot, and the fewest columns that add up to equal z dot. And that's a sparse regression problem. When I say fewest, that means we're going to have a sparsity penalty on our regression. We're going to do the same least squares regression, but we're going to add a sparsity penalty, okay? And so when you do this sparse regression, and 20 years ago, this would have been a combinatorially hard problem. 20 years ago, to find the sparsest column, set of columns that add up to x dot would mean you would have to try all sets of 2 columns, and then all sets of 3 columns, and then all sets of 4 columns until it worked. And that would be a combinatorially n choose p hard problem. That would be an NP hard problem. And only in recent years, in the last 10 or 20 years, have techniques from statistics and applied math allowed us to reliably solve the sparse regression problem in a convex optimization that scales to large problems. Okay, so really we're relying on statistics that came out of Stanford 20 years ago. Okay, and now it's like it's like a library on GitHub or in Python. Okay, so we find the sparsest, the fewest columns of theta that add up to equal x dot, and what comes out are an x term and a y term. That's what lights up when you do this regression. And lo and behold, that was what was in the x dot equation. You do the same sparse regression on the y dot equations, and you find that the fewest terms needed to explain that are y, x, and xz, which again were the terms in the original dynamics. We didn't give it the equations. All we gave it was data, and we're discovering what those equations are. Okay, you can do this in z. And so what you get when you do this sparse regression, when you assume that your answer has to be simple, you actually discover the structure and the parameters of your original nonlinear dynamical system. This is nonlinear system identification. Remember I told you in your dynamical system you want models that are interpretable and generalizable? These models are interpretable because there's only a few terms, and they're the terms that were actually in the model. They tend to be generalizable because you don't overfit as much when you penalize fitting all of your parameters. Okay? Would anyone like to ask any questions about this? Yeah.
In the matrix that you have below, all the gray columns that are not being used,
yeah,
is it like waste of computation work, or do we really need them? I mean,
oh, so those are candidate terms that could have described the nonlinear dynamics, and we don't know what the dynamics are. So we have to build theta to have lots of possibilities, and then the sparse regression selects which terms were active in the dynamics. So when our final model, everything else gets zeroed out, and we only compute the things in color here. So the final model is very efficient because there's only 7 terms being computed.
Okay, thank you.
Yep. Okay, I'm going to keep going on. So I assumed that I had access to X, Y, and Z and their derivatives. That's usually a lot to assume in system ID. You usually don't have derivatives. So what we showed, kind of the first thing we showed as a proof of concept when we developed this, was could you work on noisy measurements of your state only? So if you had X, Y, and Z and they were noisy, so this kind of fuzzy attractor, you can compute these regularized derivatives, these total variation. And if you haven't heard of total variation, please Google it. It is amazing. It'll change your life if you have noisy data, okay? This was developed in the 80s for image cleaning, okay? And it's like 10,000 citation paper. The derivative version of it is really useful for noisy time series data. And if you had this noisy data and computed these approximate derivatives and plugged those into this algorithm, you still obtain the right structural form of the equation. All of the terms are actually quite accurate except for this term here, which is off by about 20%. And I can't tell you why. But it doesn't matter that much, obviously, because you still get the right attractor. Okay, good. So you can discover nonlinear dynamical systems kind of in the same spirit of what we're doing in DMD and eDMD, but now you can use it to discover the actual vector field F itself. Okay. You can also use this to discover partial differential equations. So we decided that we would try this on all of the classical PDEs for mathematical physics. So we have our Navier-Stokes data from a code, and I measure velocity and vorticity at points in space and time. And so again, I can compute this big matrix now of partial derivatives, not just of derivatives, but of u sub x's and grad u's and things like that. And again, I'm going to try to find the fewest partial derivatives, nonlinear combinations of these that equals, in this case, the time derivative of my vorticity. Okay? And when you apply this sparse regression algorithm, this is what you discover. This is the system identification model, is the Navier-Stokes equations, and the Reynolds number is within about 1%. Okay, so you can discover PDEs with this basic idea now. And here we just rediscovered Navier-Stokes. We knew Navier-Stokes. But you could also use this to discover coarse-grained models of your PDE from data, from experimental data. People have done that now. A group at Stanford and SLAC is doing this for plasma systems where they don't actually have perfect models. They don't have the Navier-Stokes equations for their kind of non-equilibrium, unsteady MHD, and so they're trying to discover correction terms for their models, closure terms, okay? And since in PDEs we have such a vast amount of spatial temporal data, you can also get away with dramatically downsampling in space and time, and even if you only select a very small subset of the data and do this regression, you still recover the right dynamics, okay? Okay, good. So something else I want to tell you about is this kind of idea. This is the optimization problem we're trying to solve. So Bernd alluded to this earlier, and I want to just really reiterate all of the problems we have in system identification, model reduction, and control theory are optimization problems. And you have to write down the right optimization problem. That's where all the magic happens. That's where all of your human expertise comes in, okay? And our optimization problem is this. So we want a really good fit of our model. We want our model is basically this set of coefficients Xi, which tells us which terms are active in the dynamics. And I want a really good model fit that agrees very closely with my derivative matrix. But I want as few terms in that Xi matrix as possible. I want the best fit with the fewest number of terms. So I'm balancing accuracy and complexity. Okay, and this zero norm literally counts how many non-zero elements there are. That's the zero norm. And so this lambda knob, I can make lambda bigger or smaller, and I can promote more complex models or more sparse models. And so this is what that looks like, is you have these kind of complexity and error axes, and you're trying to find the sweet spot in this, and you're going to be sweeping through this lambda parameter to get more complex and less complex models. So I could have a very, very simple model, x dot equals 0, but it has terrible error. That's an underfit model, right? But it is low complexity, high error. I could do a least squares regression. Actually, this is kind of the most obvious thing you would think to do, is don't penalize sparsity at all, just do a least squares regression. That's what DMD would do. And you would get a little bit of activity in all of these coefficients. Least squares spreads out the term so that everybody would have a little bit of activity, and that would minimize your error. So it would actually have the lowest error solution, but we know that that would be overfit to the training data. Okay, I don't believe that a model with 81 terms is the right model, even if it gives me lower error on my training data. And so you hope that there's a family of models between them where you can kind of tune which model you get based on lambda. And you actually hope it looks like this, where there's some sweet spot where you have low complexity and low error. Okay? And you always have to check your system identification model on a holdout data set that you didn't use to train your model. So in machine learning, we call that cross-validation or validation, okay? And it's as important as a convergent study in numerical CFD, okay? And when you do the cross-validated error, you'll see very quickly that the least squares solution is in fact overfit, okay? And so here are the sweet spot where you can get these kind of models that balance complexity and accuracy. So that's what you're trying to do here. Okay, so there's a few things that are particularly challenging. It turns out that the regression problem is easy to solve. That's the easiest part of it. The two things that are difficult are building the right function library. Like, how did I know that polynomials are the right things to use? I mean, I completely cheated because I knew that I was simulating data from the Lorentz system and it was a polynomial. In lots of systems, you generally know what category of physics you're dealing with. Navier-Stokes equations have quadratic nonlinearities, right? We know what our Galerkin projection models look like. They look like linear plus quadratic. So I know that I can build linear plus quadratic models and probably get something reasonable for fluids. If I'm dealing with the nonlinear Schrodinger equation, if I'm dealing with nonlinear optics, I'm going to have a different set of basis functions. I'm going to have, u mod u squareds and things like that. Okay, and so for different physics, you would have guidance on how to build this library in kind of an agnostic way. Okay, so it's hard, but it's not impossible. The thing that's really, really, really hard, how did I know that X, Y, and Z were the right measurements of my system? In the Lorentz system, Lorentz actually handpicked X, Y, and Z. Those were not at all obvious as the right coordinates. The reason he has a paper that is so famous today is because he picked X, Y, and Z. Okay? So the picking of the coordinates is probably the hardest part that no one ever talks about. And it's related to Koopman. It's related to everything we're talking about, and it's very, very hard. And that's where a lot of the best research is going in right now, is how do you find the right coordinate system so that these dynamics become sparse and can be represented easily. Okay, and that's not always obvious at all. Okay, good. Couple of interesting papers. There's an optimization framework to solve this really efficiently now. And there's also lots of other awesome work, in related avenues of parsimonious modeling. Okay, good. Trying to think of what to tell you about next. So there's so much I could tell you about in this. I won't have time to tell you about time delay coordinates, but maybe I'll just tell you very, very briefly now. If I didn't have access to X, Y, and Z, but instead I just had access to, let's say, I just had access to X. This is much more common. Okay, so my wife is a neuroscientist. They put probes into brains and they measure whatever they can pick up. And they're sure as hell not measuring the full state of the system, right? They're measuring a tiny, tiny fraction of the full state of the system. And they're trying to figure out something about the system, okay? So this is a very, very brief kind of idea of what you can do when you have limited data, but you still want to build a model. So you measure X, you have no idea if it's a good measurement or a bad measurement or sufficient or not sufficient, okay? You compute X and X dot. And then what you can do is build a Hankel matrix. So you take X at time 1, time 2, time 3, this is your trajectory on the first row. And then you build a second row, which is that trajectory shifted 1 delta t in time. This is a lot like DMD. You shift it 1 delta t in time, then you shift it 2 delta t's, 3 delta t's, q delta t's, and you build this thing called a Hankel matrix. Okay? How many of you have seen Hankel matrices before? So this is actually how classical system identification was done in the 80s. Okay, the eigensystem realization algorithm, the singular spectrum analysis, they did the same thing but for linear systems. So it's really interesting to take a linear dynamical system and think about what it would look like if you wrote it in this Hankel form. Okay? And that's like 30 years of classic system identification. We're doing it for nonlinear systems like the Lorentz equations now. Okay? So you have this Hankel matrix. You've taken your one-dimensional measurement and you've augmented it into a time delay vector evolving in time. And now what you can do is you can take the SVD of this thing, POD, PCA, whatever you like. They're all the same. So you take the SVD, and now what you have is a matrix U and V. These are eigen time histories. They're eigen time delays in U and eigen time series in V. Okay, we've known since 1980 this Tokens theorem that says that if you pick the right one-dimensional measurement, like X, that if you build these time delay measurements, you get an attractor that is diffeomorphic to the original attractor. It has kind of the same information in it, but it's a coordinate transformation away. Okay, now here's what's really interesting. We were doing this with a sparse identification of nonlinear dynamics. We were trying to see, could we do this if we only had a measurement of X? So we built this Hankel matrix, we took the SVD, we got these delay coordinates, V1, V2, and V3, and we tried to do SINDI on these coordinates. We tried to build that nonlinear model. And what we found was that every model we tried turned out to be linear, which was completely confusing and very surprising and awesome, because we accidentally discovered that when you time delay your measurement, it linearizes the dynamics. And when it linearizes the dynamics, you should be thinking of Koopman theory. And here's how the Koopman connection works. So K is my Koopman operator. Every column is my previous column advanced one time step in the future. Every column is Koopman times the last column. And so if I have this big matrix and I SVD it, then I can get an invariant subspace to within machine precision so that every column is a linear combination of U, which means every, I have this invariant, this subspace that's invariant to the Koopman operator. I can hit it with Koopman as much as I want, and it's still spanned by the columns of U. That's a Koopman invariant subspace. That's what we were having a hard time finding. And apparently, if you take time delays of your data, you get it for free. Very interesting. We're still trying to figure out the ramifications of this. It works for continuous spectrum problems like the Lorentz system. Very strange. Okay. So that's really just not enough to even remotely kind of tell you about all that there is in system identification. It's getting close to 5, and I realize that tomorrow we're going to talk about fluids, and tonight we're going to drink fluids, and I don't want to delay our drinking of fluids. But I want to just take a step back. There are a few key challenges in system identification. Obviously, discovering F. You could make an assumption about what F is or not, but system identification of F is a big deal. Oftentimes, you're trying to find coordinates where you can get a simple representation of F. So those coordinates could be related to Koopman. You could use DMD to find them. You could use time delays to find them. And there's lots and lots of other considerations. I haven't told you about how you use these for control. That's a huge field. But there's a lot of interesting stuff here, and there is plenty more to do, lots of good careers waiting in nonlinear system identification. Okay, I'm going to stop there, and I have a couple minutes for questions.
I agree with all your challenges, and I would add another one: how to find your X, your state.
Yeah, absolutely. I mean, that's kind of the whole problem here is what if we measured the wrong thing or didn't measure enough? Building that state X. Time delays is one approach. Neural networks is another approach I'll talk about tomorrow. Not necessarily the best approach, but another approach. Yeah, but finding the coordinates and the right measurements are absolutely vital.
And the next thing is you have to choose X that you don't have false neighbors. So this is the empirical criterion. And the idea of the X is it allows you to integrate into the future. And the X may be too small or too large, or it must have a minimality condition to exclude nearest neighbors.
So this is a really, really good point. Remember our pendulum example? How we were trying to build a minimal state to describe the pendulum and theta wasn't not enough because I could be passing through this way or this way. If I took theta and theta one time step ago, it is enough because that tells me am I going this way or this way. So theta and a time delay of theta is also a sufficient state of the system. So to some extent, you can get rid of this kind of nearest neighbor confusion by using time delays. Good. Other questions or comments? In the back?
Thanks for a nice talk. This is the first time I heard about Cindy, and I'm kind of, after hearing what it's capable of doing, I'm a little surprised that you haven't presented an example where you accidentally found a reduced order model for something.
Oh, that's tomorrow.
Okay, sorry.
Yeah, so I usually go straight into the fluids application because that's where it shines the most because the dynamics are polynomial generally. But I decided I would talk about that tomorrow as an example of how you can bake in known conservation laws and symmetries to machine learning models. So I'll talk all about that tomorrow. But you can use this to discover reduced order models. We've done that with Jean-Christophe Loiseau and Berendt and others for fluid systems.
Is it just one other question? Is it dependent therefore on your basis functions, on whether or not you do discover a reduced order model or not?
Absolutely. Absolutely. What normally happens is you try different basis functions and it fails, it fails, it fails, it fails. And when you get the right basis function and the right measurements, it just clicks into place and you get a sparse model that's accurate. You definitely know when it works and you know when it doesn't work. Yeah.
Thank you.
Mm-hmm.
Maybe I have a very quick one, a naive question, let's say, on this Hankel matrix formulation. I see you're giving a lot of weight to T1 in this construction. How sensitive does this becomes to T1?
So technically I could shuffle all of the columns of this and it wouldn't change any of the U modes. So this is so that's the weird thing about the SVD is that I could permute all of the columns and U wouldn't change. Or I could permute all of the rows and V would not change. And so to some weird extent, it's not emphasizing T1 as much as it looks like. So as long as you have, especially in these mixing systems where the more data you collect, the more information you get, you could really start from any time, and just as long as you collect enough data that you've covered the attractor, you're going to be fine.
So, but shall we say that this can only work for a stationary condition? If I have an evolving thing or something that...
Yeah, I don't think this would work for systems that are evolving in time. Or at least we haven't clearly, trying to think if that's true, if we've demonstrated any cases. You know, I actually applied this to the stock market data, to the S&P 500. We were driving through California. This was the summer before Trump was elected. And I applied this to the S&P 500 index and, you know, looking for anomalies. And what I found, I didn't believe, and we didn't include it in the paper, but it would be interesting. You should try it. That's an example of a data set that's non-stationary. It's evolving, and it's massively forced, and the parameters are always changing. But no, it's not obvious how you would do this on those systems. Sorry? Oh yeah, I can't. So I haven't told you the last part of this, that you can actually get a linear regression model for how these time series evolve. And when you do this, you can model the first R of the R-1 of the eigentime delay coordinates very accurately, but the last one never fits very well. And if you look at this last forcing signature, it's usually almost 0, and then it turns on and becomes active when the trajectory switches to the other lobe. So what we find is that our models have this bursting signal when we have phenomenological switching or bursting. So you can apply this to like disease systems, measles outbreaks. You can basically measure the magnitude of the measles outbreak by the magnitude of this last forcing signature. You can predict when the Earth's magnetic field is going to switch based on the by the magnitude of this forcing signature. So when I was applying this to the S&P 500 stock index, I was looking for major crashes. I subtracted out the mean and and I didn't even subtract out the linear growth. I was looking for spiking signatures as precursors to crashes. And so you could actually find a lot of bursting activity before the last 2 crashes. Yes?
I've really enjoyed your talk. One scenario would be, in quotation marks, your nightmare. Suppose you have a complex system, and say one system is a Lorentz attractor, 3 coordinates, x, y, z, and the other thing is something like say a Silnikov instability, and then you have one way going from the Silnikov instability to the Lorentz attractor, and one from the Lorentz attractor to the Silnikov instability. So now you have the problem that you have some good coordinates for one attractor, some good coordinates on the other attractors, one-dimensional expressways in between them, and I would argue this would be the more generic case for complex systems, and I could give examples for that. So how would you, in quotation marks, partition your state space to find the right local coordinate systems?
It's a really good question. It's one we've actually thought a lot about. So again, not an intro question. What Barent's asking, I believe, is that for most complex systems in reality, you have lots of local attractors, and you have switching between these attractors. How would you model that? I would argue that what you really want to do is a hybrid deterministic and probabilistic model. Probabilistic for the switching, deterministic within each basin, and probabilistic for how they bounce between that. That's what Frank Noe and Schutte do for their molecular dynamic systems. I think that's what we should be doing for our turbulent systems. A catalog. So probabilistic bouncing around the catalog, and then deterministic inside. That's what we're trying, but it's tricky. Okay, it is like well into everyone's afternoon beer time, and I am not going to deprive you of that. So
let's go for a beer then.